Okay, so here we have this circle again, and let's look at this so-called set of equations. Now this is not, there's no vector stuff here at all, okay? But this is obviously two equations. So let's just look at them, and we can see that the input variable here is t, and the output is x in this one, and here it's t, and the output is y. Okay, so we have two equations, one with an input of t and y, and x is the output, and the other with y as the output. Okay, so what's going on here? Well, let's think of t as time. So, t can be 0, or t can be something greater than 0. So we're going to say that t can be greater than or equal to 0, and it goes up to some number. In this case, kind of a weird number. We don't have to worry about that. But it goes, let's saying we're restricting the time to be greater than 0 and less than something else. Okay, so anyway, as we increase t, then it's clear, since we have two equations here, that x changes and y also changes. So let's put in t equals 0, and what do we get out? So when t equals 0, we're going to get an x and we're going to get a y. Okay, good. So what are we going to get? So the cosine of 0 is 1, and the sine of 0 is 0. So if we put in t equals 0, we get 1 here, so we get 2 times 1. And here we get 0 here, so we get 2 times 0. So in other words, we get 2 for x and 0 for y. So if we think of that as the coordinates of a point, then when t equals 0, x is 2 and y is 0. And that could be here, right here. If this distance is 2, then that would be right here. Okay, so we have that. Okay, now t can increase. I mean, t is a variable, so we're going to let it increase. We're not going to let it decrease, but it could decrease also. But they're saying keep t greater than 0. So we could put in some other t. So now, what should we put in? Okay, so now maybe it makes sense. Just now we can sort of see why they're using these weird numbers, like pi over 2, because the cosine of pi over 2 means the cosine of 90 degrees. We could put in degrees, but we don't usually use degrees. So if we were writing as just degrees, then we could put 90 in here, and we would know the answer to the cosine of 90 degrees and the sine of 90 degrees. But usually, well, anyway, they're not using that. So they're using pi over 2, but you hopefully know that the whole circle is 2 pi, right? Or in this case, it's actually 4 pi because this is radius of 2. But generally speaking, the whole circle is if it was a unit circle, the whole circle would be 2 pi. And then, half of that is pi. And half of that is pi over 2. So that kind of shows us why, pi over 2 might be a good value to put into here. So let's put in pi over 2. So when we do that, we're really asking for the cosine of 90 degrees, which is 0, and the sine of 90 degrees, which is 1. But anyway, we're using pi over 2 instead of 90 degrees. So that's what we get. So we get 2 times 0 and 2 times 1. So x is 0 and y is 1. Sorry, x is 0 and y is 2. So then where are we? When t is pi over 2, we're up here. If this is, again, going back to this is radius 2, then we're right up here. This is 0, comma 2. Okay, so you see that as we change t, we're going to different places. Now, it's not completely obvious that we'd be following this particular path when going from here to here, but it turns out to be true, that we do follow this path when going from here to here. Maybe, you might think, oh, you go this way and then over here, because all we did was check these 2 points, and we found, yeah, you are here when t equals 0. When you go to t equals pi over 2, you are here, but who knows how you get there? It could go all over the place, but no. turns out that actually these two equations, you know, for any t, you get a pair of x and y, and it turns out that every pair of x and y is going to be on this line, and that you will be moving along that line. So that's not obvious, but it is true. So anyway, um, so that's the point though. So here, as t moves, as t changes, x and y both change, and so we move around in the plane. In this case, we move along the circle, but generally we just move around in the plane because x and y would be changing. So that's what this is about up here. They're not saying specifically what the function is. Here they are saying specifically what the function is, but in general, we just have any function of t for x and any function of t for y. So that means as t changes, you go all over the place because x and y change, and you move around. So, okay, so that is, so these, in both cases here, the general case up here, and this is an example of the general case where specifically we have, for f we have this, and for g we have this. These are called parametric equations for a path or for a curve. So, as we move t, we're going to go all over the place. If it's just these, we don't know where you're going to go. And specifically here, as you move t, you go around the circle, or that's what they claim in the book. Maybe they haven't shown us that, but that's what they claim. So let's read this. First, we remark that a curve in the plane may be described, analytically means with equations, by points. Yep, that's for sure. A curve may be defined by points, x and y, where x and y are given as functions of a third variable, the parameter. So t is called the parameter in this discussion. So as t changes, we get different value for x, different value for y, means we get different point. These functions of t give rise to what are called parametric equations for the curve, because we have the function equals x, the function equals y. That means when you equals, and you don't just have the equation, you don't just have the function, you have an equation when you write equals. You don't just have the function g, you have an equation when you write equals. So they say these functions give rise to parametric equations for the curve. And then they give us a specific f and a specific g here. And they claim that we get this here. And one of the ways to sort of show that is to show that this actually is a circle, is to take x squared plus y squared and show that it's a constant. So if x squared plus y squared is a constant, like if it's 4, we know it's a circle. If it's 4, we know it's a circle of radius 2. If it's a constant, in general, it's a circle. Might be, the radius might not be as simple as just the square root of 4, which is 2. It might be like square root of 3, which we don't know what it is, but it's still going to be a circle of radius square root of 3. So, and that's true here. If we take x squared plus y squared, we're taking this squared plus this squared, and if you just work this out, do they do it? No, they don't do it. But if you just work this out, you're going to get 2 times this squared plus, anyway, you work it out, and you'll see that you get 4. So that means that you're always on a circle. Now, it doesn't show that we actually go along this path, so that requires some more discussion, I guess. But at least we know we're never off of this circle because we're always in the state where x squared plus y squared is equal to 4. That means we're always on a circle. But it doesn't show, actually, that we're moving. Maybe we go like this, and then we come back here, then we go back up here. Who knows, right? But anyway, we're never leaving the circle according to this argument. Okay, so these are called, as we said, the parametric equations for this circle. Actually, we have to say a set of parametric equations. First of all, it's more than one, but also I use the word a because there are other possibilities to describe the same path here. Okay, but we'll call them a set of parametric equations for this curve or for this circle. And more generally speaking, we would write it like this, a set of parametric equations where we are not specifying what the curve is and what the particular set of functions are that give these equations. And then using this framework, we can talk about curves in 3D as well. So that's something that we really couldn't accomplish very easily without using parametric equations. But now that we have this concept of parametric equations, we can get the equations for a curve in 3D or in R3. Now we did have a single equation, but it didn't describe a curve, it described a plane. But with this framework, we can describe a curve in 3D. Okay, so she says the advantages of using parametric equations are twofold. First, they offer a uniform way of describing curves in any number of dimensions. So we saw that it was very easy to go from 2 dimensions to 3 dimensions, and of course we could go to 4 dimensions. We just need one more equation here, or however many dimensions we want. Okay, so that's one advantage. And the other advantage is that we saw that they imply a kind of a direction of a curve. Now, we don't have anything like that when we do a standard definition of a curve, like when we define a circle as x squared plus y squared equals 4, that we don't have anything like the concept of a direction. So maybe we don't care about the concept of a direction, but sometimes we might, and this method gives us at least that ability to talk about the direction of the curve, if that's something we want. Of course, that direction comes from the fact that we're assuming that t goes from 0 to 2 pi. For example, if we assumed t was going from 2 pi to 0, then it would be the opposite direction. So it's really a function of this part here and the assumption that t is increasing. Then we get a direction. Okay, so the next thing we're going to do is talk about another way to provide equations for lines. So we're going to focus specifically on lines here. So, for example, this picture here. So typically when we talk about a line, we talk about determining a line, say, using 2 points in the plane, or 2 points even in space, right? We say 2 points determine a line, and so if you give me 2 points, I can tell you the equation of the line. But here we're not going to be given 2 points. Here we're only going to be given 1 point, but we are, of course, going to be given another piece of information, because if we were just given 1 point, there's not a single line that passes through this point. So just being given a point is not going to get us anywhere near getting the equation for a line, because there are many different lines. So what else are we going to be given? We're going to say we want the line that goes through the point, for example, this point P0, and is parallel to a given vector. So here's a given vector, and suppose we want it to be parallel to this vector and go through this point. Then it seems clear that there's only going to be one line that satisfies those two conditions. So in this picture, we would say it was this line here. The question is, how can we write the equation of that line? Let's go back and think about this question, which we've done in, what was it? I don't know, when we were like 10 years old or even younger than that, we were able to do this. So find the equation of a line that goes through the point 2, 4 and has slope 3. So how do we do that? So that means we want the equation of the line that goes through like this point here, 2 comma 4, and has a slope of 3, which I'll just try and draw something like that. So find the equation of this line, for example. Goes through 2 comma 4 and has a slope of 3. So one way to do this is just to write y minus 4 over x minus 2 equals 3, because that tells you that change in y over the change in x should be 3, and then you can solve for y, and you get a more standard form of the equation, but this is good enough, actually. But the point I wanted to make here is that, I put in, usually we write y1 minus y2, x2 minus, I'm sorry, x1 minus x2. But we didn't fill in this value and this value. Of course, we don't fill in either of those values, but I just want to emphasize that right now. We leave those free, and why do we do that? Because we're trying to find the equation for a line so that any point on the line, we're trying to write an equation, and then we fill in the y and the x, and that point should generate a point on the line. And any point on the line, we would fill in the y and the x, and we would get this would be true. So we don't fill in the x and the y. We leave them open like this. That's the standard thing that we do, but I just wanted to emphasize that here. So we write this equation so that we can find any point on the line using this equation. So any x comma y. Now, going back to here, we want to do the same thing. So we said that we wanted to go through this point, and we want it to be parallel to this vector. And then we want to write an equation so that any point on this line will satisfy the equation that we write. But we're given kind of different circumstances here. We're given a point and a vector. But it's kind of like being given a point and the slope, right? Because a vector sort of indicates the slope. But anyway, we're given a point and a vector. Okay, but we're used to saying that we should be able to switch between points, a point of view, and a vector point of view. So I want to be able to find the equation so that any point on this line will satisfy that equation. But I can also say I want to find the equation such that any vector pointing to that point satisfies the equation. So instead of thinking about the point, I'm just going to sort of identify it with the vector. We're going to call this vector r. So it's going to point to some arbitrary point on the line. And here we can see that picture here. So we still have the point P0. We still have the vector A that's supposed to be parallel. We also drew A over here, but remember we're allowed to translate it. So they've translated it over to here. And then instead of thinking of the point P, we're going to think of the vector that goes from the origin to P, which we can write this way, OP. Anyway, it's this vector. So we want to write an equation for any arbitrary vector r, which points to a point on our line. Okay, so here's the vector that we're trying to find. And what are we given? We're given P0 and we're given A. But again, we should be able to switch from the point of view, in other words, thinking about this point P0, and the vector that points to that point P0. So what is that vector called? Well, it's here, OP, and they're calling it B. It's OP, but we'll just call it B. And again, what are we trying to get? We're trying to get R. So what's the relationship here? How can we write what R is equal to? Well, we can write it as a sum. A sum of what? A sum of two vectors. Which two vectors? This vector plus some multiple of A. It's not going to be necessarily exactly A, but some multiple of A. So and that's clear that we can get to R by going this way. So that's b, and then adding some multiple of a, adding ta. So we can say that r is equal to OP, which is b, plus ta. So that's what they write here. R, okay, R is clearly, this R is clearly a function of t, right? Depending on the t, we'll get different points, but if we want to get to this particular one, it's going to be a specific t, but in general, we're going to depend on the t. So we shouldn't object to them saying R of t, because R certainly depends on t. But anyway, we can leave that out if you don't want to see that. You don't have to write that part there. We can just say R equals, this R equals this plus some multiple of A. R equals B plus TA. So this isn't the normal way that we're used to writing equations of lines, but it's true, it works, right? Depending on what t we put in, we can get any point on this line. We can even go to this side of the point P0 if we put in a negative number for t. So we can get any point on this line by varying t and doing this vector addition. It is vector addition because this is a vector and TA is a vector, so that's vector addition. And that's good because we want to get a vector, r. So in order, when you add two vectors, you get another vector. So it's good that we're adding two vectors and we are getting our vector r. So this is what they wrote here, but at first they called it, instead of calling it b, they called it OP. And b goes from O to P, and we need coordinates for P0, or we want to discuss we want to give some names for the coordinates of P0. So since we're calling this b, we'll call the coordinates B1, B2, B3, which is what they've done here. And then if we want, we can express OP0. Of course, we said we can express it as b, but we can now, if we have the coordinates of b, or the coordinates of the point P0, we can write it as B1I plus B2J plus B3K. So we said that we should be able to switch from this to this and from this back to this without thinking about it too much. And we're also going to say that A, remember here's A, and we also here, and A is has some coordinates, so we may as well call them A1, A2, A3. And so we can write A with A1, A2, A3, but we can also hopefully switch to this without much difficulty. And so finally, again, we get this equation. Now they call it a parametric equation, and that's because up here the parameter was called t, and t. The parameter was called t and t. The parameter was called t, right? That's called the parameter. And this also has a parameter, the same t. But so we can call this a parametric equation as well, because there's a parameter in it called t. So what's a parameter? It's kind of just like a variable, but they kind of use it in a specialized way, at least here. So anyway, this is called a parametric equation, but we can be a little bit more clear. We can call it a vector parametric equation because it is a vector equation, and it also has parameters in it. So we can, or a parameter in it. So we can call it a vector parametric equation. Now the next part is a little bit interesting. So this vector equation actually can be written as a set of non-vector equations. And that comes all the way back from here. Basically, the first thing we said about vectors was how do we say that two vectors are equal? So if we say A and B are equal, what does it mean? It means that A1 equals B1 and A2 equals B2. So when we say two things are equal and they're vectors, we actually get two equations here because there are two elements here. If this was in R3, we would get three equations. But anyway, for R2, we get two equations if we say that two vectors are equal. Well, that's exactly what we're saying now. This is our vector equation, but it's equating the left side and the right side. And the left side is a vector, and the right side is also a vector after we add these up. So it's a vector equaling another vector, and that's going to generate multiple equations. If this is in R2, it's going to generate two equations. If this is in R3, it's going to generate three equations. Let's see that. To do that, we can re-expand this as in terms of ijk, and we can re-expand this in terms of ijk. So let's do that. But just a quick reminder, we said that we want the point P to be kind of general. It can be any point. So we don't want to call it like x0, y0, z0. We try and indicate that's kind of general by just calling it x, comma, y, comma, z. But for OP and A, we have already the coordinates. So we said OP is like this, and A is like this. And so we'll leave the left-hand side as it is for the moment, but we'll write OP as the sum of B, this part is B, and then T, and this part is A. And now what we can do, of course, is we can say that all the multipliers of I, which in this case is B1 and A1 times T, we can collect those, and all the multipliers of J, which is B2 and A2 times T, and we can collect those, and the same thing here, we can collect these. So we get, on the left side we haven't done anything, but on the right side we have this. Okay, now R or OP, this is R or OP, we can write it as, like we said, the coordinates are going to be general, just X, Y, and Z. And now we have, on the left-hand side we have I, J, and K. And on the right-hand side we have I, J, and K. And so we equate the i's on the left with the coefficients of I on the left with the coefficient of I on the right. And this is going to give us the three different equations. So on the left we just have x, but on the right we have this. We get x equals this, y equals this, and z equals that. And so now we have the parametric equations in the kind of original form that we discussed parametric equations. Parametric equations, three parametric equations for a curve in 3 space. So we also had the vector equation, and that's just one, but really we could say that it represents these three, or these three represent the vector equation. So they're equivalent, and we can express it either way. So this is kind of more compact, but it really represents three equations if we're in R3. If we were in R4, it would represent four equations, and if we're in R2, it would represent two equations. And if we are in Rn, we would get n equations. So we have the parametric equations for a line in n space. Okay, if we want to try an example of this, we should be given a point, and we should be given an A. So they give us a point and an A here. So they say, find the parametric equations of the line through this point and parallel to this vector. She seems to make a habit of putting confusing things as coefficients sometimes, like pi. But anyway, it's just a number times I, another number times j, and another number times k. I guess we could say this number is -3. So anyway, we have a point, and we have a vector that we want the line to be parallel to. And we want that to go through this point. So, so A is this, and B is this. So B is the point, so it's 1, negative 2, comma 3. It comes out to this. And the vector is here. And so we can write the vector form like this. It's r equals, this part is b, and this part is a. And then we can collect those, collect the coefficients of I, of j, and k. And then we just equate the left hand side coefficients of I, j, and k with the right hand side coefficients of I, j, and k. We get x equals this, y equals this, and z equals this. So we get that. Remember again that we're calling the arbitrary point P, we're talking about the coordinates as as x, y, and z instead of putting like an x0 there, right? And then these are the multipliers of the corresponding, the other way of viewing this, which is the ijk way. So we get xi, yj, and zk. And so that's what we have here. Okay, I won't go through this one, but let's just read it. So they instead of giving us what they gave us just earlier, which was a point and a vector, now they're going to give us 2 points, not a vector. They're not going to give us a vector. They're going to say, suppose it goes through P0 and some other point P1, and then ask us to sort of go to get to the same result that we got just now with the parametric equations and the vector parametric equation, but they're not giving us the vector. But anyway, that's easy to do because if we have 2 points, we can figure out a vector that is going to be parallel to our line, and then we can just go from there and do what we did here. So I won't go through it, but if you want to, you can stop this and read that. Sorry, you can stop this and read this. And you can read this. Now they bring up the point that we were given a vector, A, that the line should be parallel to. For example, in the first picture, this is A. But, you know, they didn't have to give us this A. They could have given us a different A. As long as it's in the same direction as this A, we should be able to get an equation. But we're actually going to get a different set of equations when we use a different A. So that's an important point, that the equations that we get are not unique. We could get different equations for the same line or for the same curve. So they are not unique. So she said, well, how can you be sure that if you get one set of equations or you get another set that you're referring to the same line? And she says, well, you can, one thing you can do is produce 2 points that lie on the line specified by the first set of parametric equations and see that these same points lie on the line given by the second. So that would ensure that that they both sets of parametric equations refer to the same line. But there's also another way, and that is using what's called the symmetric form of a line in R3. So these methods don't work for curves that are not lines, but if they are lines, this method and the previous one we just mentioned work. So the idea is that we just solve each of these, this equation, this equation, this equation, for t. So we'll get t equals something, get t equals something, t equals something. So if we do that, we get this. T equals one thing, another, and another from the 3 different equations. And then you can obviously set these all equal to each other because they're all equal to t. So we eliminate t. So we sort of lost the direction then, right? Because t was the thing that gave us the direction of the curve. But anyway, that's not what we're trying to do here. We're just trying to kind of express a general form for the curve involved, or the straight line involved, sorry. And this is called the symmetric form for the equation of the line. Now, it's not called the symmetric form for the parametric equations of the line because the parameter is gone. But anyway, this is called the symmetric form. Now, the symmetric form is actually not just one equation, right? We actually have two equations. We're saying that this equals this, and we're saying that this equals this. So it's actually two equations. Now if we go back to the previous example, which we didn't, their previous example, which we didn't actually do, but here um, they asked us to find through these 2 points, the line. And these were the parametric equations that we got. And actually, they showed that you could get two different sets of parametric equations. We didn't do this, but you could get two depending on, for example, um, what A that you use. So you can get different sets of parametric equations, and they did get two different sets of parametric equations here. So we can test this out by solving for t in each one of these, and we'll generate a symmetric form. And we can also do the same thing here, solve for t, and get the corresponding symmetric form, and hopefully they will be the same symmetric form because they said that the symmetric form is unique. So that's what they do here. Now these don't exactly look unique, but you can do a little bit of algebra on them and get um, the same. You'll see that they're the same. So here they describe the algebra that you can do. And then here they point out that actually when you have the symmetric form, it's actually two different sets of equations, like we said. Okay, so next they're going to give us two examples where we use parametric equations for some convenient tasks. So the first one is here, identify the intersection of a line and a plane. So they're going to give us the equation of a plane, and they're going to give us the equation of a line, and we want to find the intersection if it exists. And typically, if you just think of a plane and then you think of a line, they probably intersect, but they don't have to. They could be kind of parallel, but they probably intersect. So they're going to give us, they're going to specify a plane, and they're going to specify a line. So they're going to specify the plane using this kind of form. So this gives us a plane. And I think we discussed that already. And then they're also going to give us this, and we've just talked about how this is the set of parametric equations for a line. So remember, for this set of equations for the line, each coordinate depends on t, and given a particular t, we get a particular point because we get a particular x, y, and z on the line. So we could say that we want to find the t, which gives us the point on the line which intersects this plane. So it's kind of like to solve for t somehow. And what we could do is we could just take these values of x, y, and z, and those are x, y, and z, and we could replace x by this part, and y by this part, and z by this part. And then we're going to have, instead of an equation here of x, y, and z, we're going to have an equation for just t. And presumably we can solve that for t. And so that's exactly what they do here. And then they solve it for t. So that's probably not that hard. And it turns out that they find out that t is equal to -2. And then we want to verify that this actually makes sense or that this actually worked. So we can put in t equals -2 into here. And that's going to give us a certain x, y, and z here. In other words, it's going to specify a point. And of course, we'll know that that point is on this line because we put in the t and we got that point. But how do we know that that point is also in the plane? And then we just put those coordinates into here. And if this is true for that x, y, and z, that means that point is also in this plane. And so that's what they do. They find that this is the point, and then they put that into here, and it works. Okay, the next task that we wanted to do was identify the intersection of two lines. So they're going to give us two lines, and they're going to give us the parametric equations for those two lines. So here they are. They're going to give us, this is a line, we already kind of accept that, and this is another line. We have two lines here, and we'd like to know whether they intersect, because they don't have to intersect, and especially in three dimensions, they don't have to intersect. So we'd like to know whether they intersect, and if they do, we'd like to know where it is that they intersect. That is, we want to know the point. That is, we want to know the x, y, and z that denote that point. Okay, so if they intersect, that means they have a point in common. That means that there's a t that we can put in here that will give us an x, y, z. And there's a different t, could be the same, but it's not going to be the same. But there's another t that will give us the same x, y, and z. That means they both contain the same point. So we'll say there's a t1 here that gives us x, y, and z, and there's a t2 here that gives us the same x, y, and z. So if we're getting the same x, y, and z, then we can say that when we put the t1 into here, we're going to get the same thing as when we put the t2 into here. So that's what they have here, and the same thing for the y, and the same thing for the z coordinate. So now we actually have three equations with two unknowns. So that could mean that there's no solution because we have more conditions than we have unknowns or variables. So it's kind of more likely that there's no solution than that there is a solution. But there could be a solution, and that would require us to know what the T1 and the T2 are. So they do some algebra here, and they find out that T1 is equal to that there is a T1 and a T2, and that they are -1 and 1. So it didn't have to be a T1 and a T2, but that there are two. We don't get a kind of a contradiction here. And so we can put T1 into here, or rather into here, and we can find out the coordinates of the point of intersection, or we could put T2 into here and hopefully find out the same coordinates of the point of intersection. And it turns out for these equations that this is the point of intersection, so they do intersect. Okay, so we did two examples. What were they? First one was given a line and a plane, and the plane was given here, and the line was given here, and we found the point of intersection. Now, it doesn't have to be a point of intersection between a line and a plane, but in this particular example there was. And then in the second example, we were given two lines, and they were given in this form, parametric equations, and we wanted to see if they intersected, and if so, where. And we equated, well, we said there has to be a T1 that gives us a certain point here, and a T2. It doesn't have to be the same T1 and T2. That's why they use different values. There's different variables, T1 for this and T2 here. And anyway, we want to be able to get the same XYZ point, same coordinate, using T1 here and using T2 here. And we get three equations with just two unknowns. Doesn't have to have a solution, but it did. And we found out the T1 and the T2, and they both generate this point. So there was a point of intersection between these two lines. Okay, the next section we're not going to cover, it's called parametric equations in general. So in other words, not just working with lines, but more generally just any kind of curve. And so they do some example here with a kind of crazy looking curve, which is generated from a ball which rolls, and we just focus on one point as it rolls, and as this ball rolls around, this point moves like this, and this is a pretty complicated curve, and it would be very hard to write it, it is in the xy plane, so we could try and write it as y equals a function of x, but it's very hard to do that um, for this particular curve. But if we approach it with a parametric equations approach, then it turns out to be pretty easy. So if you want to read through that, you can look at this, and you can look at, and here's the actual answer. So it would be pretty hard to get uh, without using a parametric approach. But this is the answer. Same thing, we have x as a function of t, and y also as a function of t. Okay, so section 3 is on the dot product, and they say, well, before we defined, what were the things we defined? We defined x plus y, where x and y are vectors. We also had k, where k was a scalar, times x, where x is a vector. But we didn't talk about multiplying two vectors together. So there is several ways that we can do that, several ways we can define that. We use different symbols for the different ways. So the way they're going to talk about now, they're going to use the symbol. Here we have a vector x, and then the symbol is dot. And this is called the dot product. Now, this is kind of peculiar because when we add two vectors, we get another vector, right? I emphasized that several times. And when we multiply a scalar times a vector, that just increases or decreases the size of the vector. So that gives us a new vector. So in both of these cases, the result is a vector, which is sort of what you would kind of expect, right? When you work with vectors and you do things with them, like add them or whatever you do, you kind of expect to get a new vector as the result. But here, you don't get a new vector, so that's kind of strange. But anyway, that's the way they define this. And you get a number here, not a vector. And it's also, so it's, you get a scalar instead of a vector as the outcome of this operation. And it's called dot product. They use the dot there. So they give an example here where we have a vector A in R3 and another vector B in R3. And we're going to define this dot product. It also has other names. It has called the inner product, or it's called the scalar product. Anyway, we're going to define this thing. And all we mean, if this is A and this is B, all we mean is that we do this. So what does that mean? We take this times that, and this times that, and this times that, and that's all, and we add them up. So that's what we have here, and that's called the dot product. And you can see that when you do that, like this addition is just adding two numbers, right? These are just numbers, and we multiply them, we just get a number. These are just numbers. When we multiply them, we get a number, so we're adding two numbers. It's not just adding numbers and adding numbers again. We're just going to get a number out here. So, as I said, a little bit unexpectedly, this particular manipulation, which we call the dot product, doesn't give you a vector in return. It gives you just a number. And if you have something in R2, then it's simpler. You just take the x coordinates, multiply them times each other, the y coordinates, multiply them times each other, and that's it. Add them. So here, we just give an example. So here's a vector in R3 and another vector in R3, and we do the operation like we just said to do. We get a number out. We can also write this, express this differently, the same vector, just get a different way of expressing it, the IJK version, and same thing here. This is a different example, but we can take a vector expressed in the IJK form and take another vector in the IJK form. This here, the j part is 0. And we still take the x times the x, so that's 3 times 1. And the j is 2 times 0, and the k is -1 times -2. Okay, so that's it. That's called the dot product. Now, it turns out that, there's certain things that are true about the dot product regardless of the particular vectors we're working with. So, for example, if you dot A times itself, it's always going to be, uh, it's never going to be negative, okay? Um, and that's kind of clear because if you take this times itself, then you can get 1 squared, negative 2 squared, and 5 squared. When you add those up, that negative 2 is going to be squared is going to be positive, so you're only going to get a positive thing there, or it's never going to be negative. So that's where you get this from. And the only time that A dot itself would be 0 is if A is actually 0. So anyway, these are true for any A. So these are called properties of the dot product. And then also, it doesn't matter if you switch the order. AB is the same thing as B dot A, and that's pretty obvious from the definition. So if I move this over here, it's not going to make any difference. And then we have like a kind of a distributive property here that A dot B plus C is equal to A dot B plus A dot C. Now, what's the result of this, by the way? Well, this is going to be a number because A dot some vector is a number. So this better be a number also, but I think that's pretty obvious. And then there's this property here. If you have K, scalar multiple of times A dot B, then you can bring the K outside like this, or you can move the K to the B. And then they prove property 1, which I kind of proved, and you can prove the other ones as well. Okay, now with that, we can also, we haven't defined what we mean by the length of the vector. So here they give that definition. So if A equals A1, A2, A3, the length of A, also called the norm or the magnitude of A, is denoted by this. Now this looks like the absolute value, but um, it's not the absolute value. But maybe part of the reason they use this symbol and it looks like the absolute value is that the length will, as we define it here, is never going to be negative. And that's also true of absolute values, right? But absolute values should be applied to numbers, right? That's what absolute value is for. We put in the absolute value of 2, for example, or negative 2, right? We're supposed to put a number in here. But here, we're not putting in numbers. We're putting in vectors. We have a different symbol. But one thing that holds true about this and this is always non-negative and this is always non-negative, right? Okay, anyway, what is this? What do we mean by the length of this vector? So it is this. And, let's take, instead of that, let's suppose we didn't have this here. So we only had something in R2. So what is the length of a vector? So let's say we have that vector A, like that. Of course, the length we know. We can do this squared plus this squared is the length squared. And then if we take the square root of that, we get the length. And so that's what they're doing here. They're taking A1 squared plus A2 squared, and then for 3 dimensions you have plus A3 squared, and then you take the square root of that, and that's called the length. However, looking at this, and looking back up here, what was A dot A again? Well, we know what A dot A is because we know how to do the dot product. So if we have A dot A, we get A1, A1 plus A2, A2 plus A3, A3, or A1 squared, A2 squared plus A3 squared. But that's what we see here, A1 squared, A2 squared, A3 squared. So what can we do? We can say, well, the magnitude of this vector A, which we denoted by this, and which we defined like this. But this part inside is just this part here, which we wrote as A dot A. So we can say that this is equal to the square root of A dot A. Okay? So we can say that the magnitude is that, and so this, which denotes the magnitude, is this, where this is a dot in between there. So we have this, Or if we square both sides, we have this. So we have a kind of nice handy way of talking about what the magnitude means. And it's related to the dot product. We can express it in terms of the dot product. But it really comes from this, the Pythagorean theorem, or in 3 dimensions, just another version of the Pythagorean theorem, sort of. It really comes from that, but now we can express it in terms of just the dot product. So I guess this is another reason why they use um, the something that looks like the absolute value, because that's also true of the absolute value, right? If I say the absolute value of -2, it's equal to the square root of -2 times itself. Can't write this, but -2 times itself is 4, and the square root of that is 2, and that's what this is. So it resembles this, or this resembles this. But this is not a dot product here. It's just regular multiplication because these are just regular numbers. But this is a dot product here because these are vectors. So not the same thing going on here as here, but it looks very similar. Okay, next we're going to get a very important and a kind of nice result, but let's just say important result about the dot product. And it kind of comes from thinking of these vectors geometrically. So let's think of these vectors geometrically. So here's A and here's B. So we're taking A and B and we're putting them at the same, we're putting their tails at the same place, first of all. We don't have to leave it like that. I mean, they don't have to be like that, but we can do that for any two vectors A and B. So suppose we have any two vectors A and B, and suppose we put their tails at the same place, and then there's going to be an angle between them, and that angle we're going to call theta. And suppose further that that we're only doing this for vectors that where theta is less than 90 degrees, or less than pi over 2. Or sorry, less than pi, less than 180 degrees. Okay, so we're only going to do this where where the angle is specified to be between 0 and 180 degrees, or we can also call that 0 to pi. And we're assuming, of course, that these are non-zero vectors. So we're not really interested in doing this if A is a 0 vector. It means it doesn't have any length at all. We're not really interested in that case. Okay, so we're assuming that they are non-zero vector. Because what would we call the angle between A and B if A was just the 0 vector? There's really no angle that we can talk about. They say the angle is indeterminate in that case. So suppose we have this situation, then we get this result. A dot B equals the magnitude of A times the magnitude of B. Remember, that means the length of A times the length of B times the cosine of the angle between them. So that's a very powerful result. So let's see what are some of the implications of this. Before we consider the proof of it, let's think about what would be the implications if we accept this as true. So remember cosine, if this is the unit circle and we have a line like that from the origin to some place on the circle, then the cosine of the angle here is the orange length here, right? It's this length here to this point here. It's the coordinate, it's the x-coordinate of this point, so that means it's this length here. So what happens to the cosine as we go from a 0 angle to a 90-degree angle? So when it's a 0 angle, the cosine is 1, and when we get to 90 degrees, the cosine, the x-coordinate of up here, is 0. So it goes from 1 to 0. So what does that mean about this formula here, which has the cosine of the angle between them? So if the two vectors the angle between them is 0, what does that mean if it's 0? That means they're both pointing in the same direction. So if the angle between them is 0, then the dot product is just then this part is just 1, and so the dot product is just this times this. So it's just the magnitudes of each of them multiplied. But what happens if the angle between them is 90 degrees? Then the cosine of the angle is 0. So then what? The dot product has to be 0 no matter what this part is. This is 0, so the dot product has to be 0. So this is kind of exploring something about dot products. So we kind of get a deeper understanding of what this dot product definition that we gave, which was pretty simple, right? It was just, we take this times this, that times that times that, right? Very simple, and add it up. Now we're exploring what's we get a little more insight into this. So what is that insight again? If the angle between A and B, if they point in the same direction for whatever reason, then the dot product is going to be the product of their magnitudes, the product of their lengths. But if the angle is 90 degrees, it doesn't matter how long they are, the result is just going to be 0. So dot products of vectors that are perpendicular to each other, you always get 0. Doesn't matter what their lengths are. Now that wasn't exactly evident or clear or obvious from this definition, which was here, this thing up here, but it's a fact. Well, we haven't proved that it's a fact, but it is a fact. So also we can see that this kind of the angle between them sort of inversely regulates the size of it. So as the angle opens up, the dot product sort of gets smaller, right? In other words, if you had the same vectors, A and B, the same lengths, and as you open up this angle until you get to 90 degrees, you're reducing the dot product, right? So the dot product is kind of governed by the angle between the vectors. Okay, so I would like to go through the proof, but I'm not going to. Just going to take some time, and you can read it. It's a very cute little proof here, very nice work. I would like to do it, but I won't do it. But you can read it here. So I guess the last line is they end up with this equals this. And then I guess we can cancel, right? We get A dot A. There's an A dot here, and it's a minus, so that goes away with this one. B dot B, and there's a minus, so they go away. And so we get minus A dot B and minus B dot A, but those are the same. Remember, we said that we can change the order here. We can commute these two. So we get 2A dot B over here is equal to this. Then the 2's cancel, and we get the result that we wanted, which is that A dot B equals this part here. So you have to go through all of this to see it, and I recommend that you just read it quickly and make sure you agree with it. But anyway, that would be the proof of this very interesting result, that the dot product involves the cosine of the angle between the two vectors. Okay, now as a result of that, we can write this actually. Okay, so I zoomed out here so that hopefully you can see what I just said. Well, I really had to zoom out here actually, so it might be hard to read this, but you can go from here to here. Now, except that here we have this cosine to the -1. Let's just zoom in on that. So let's just remember what that means, or let's just say what that means. So if you have something like y equals the cosine of x, then we can say this. Sorry, I had to write this like this, but we can take the cosine. This is called the inverse of the cosine. We can take the inverse of the cosine of this side and say it's equal to the inverse of the cosine of this side. So I wrote inverse of the cosine of y is equal to the inverse of the cosine of this side. But that's what the inverse of a function, that's what this means, the inverse of this cosine function. When you apply both the inverse to the function itself, it's like you end up doing nothing. So you end up with just x. So we get just on this side, we just get x. So we get what? If y equals cosine x, then x equals inverse cosine y. So that's what the inverse function means. It's the function which, when you apply it to your given function, ends up just doing nothing. The pair of them together does nothing. It's like, when you have this square function, and then, what can I do to this to have done nothing at all, to sort of undo the squaring? So obviously, I can take the square root. So we say squaring and taking the square root are inverses of each other, inverse functions. Same thing here. Cosining and inverse cosining are inverses of each other because when you do them both together, you just did nothing. Just like here, I did nothing. Okay? So that's what the inverse cosine means. And so all they did was they started with this equation, and then they moved these two pieces. First they moved these two pieces over down to below, right? We can divide by them. We get divided by these two pieces. And then they had a dot b over this stuff is equal cosine theta. And then they take the inverse cosine of this side is equal to the inverse cosine of cosine theta, which is just theta. So we get that theta equals that. So, okay, so who cares? Well, this is really cool. Why? Not particularly cool, right? We just did some very simple algebra there. It's not that cool. But it tells us what the angle is between A and B. Okay, so that's not so interesting because it's just not that interesting, especially in the sense that we already know what we mean by the angle between A and B. So we really didn't get anything out of this really so far. It's just a nice form for the angle, but that's all. It's not. There's no kind of insight here, I don't think. But what's very cool is that, remember, the dot product is defined, we talked about it for R2, vectors in R2, or vectors in R3. And we saw this very simple to go from R2 to R3 in terms of the dot product, or, yeah. But, there's no problem with taking vectors in, R5 or something. So you'd have 1, 2, 3, 4, 5 spaces for A, and also the same for B. 5 spaces, 1, 2, 3, 4, 5. No product with taking the dot product of vectors from R5, but we certainly don't have any idea of what we mean by the angle between vectors in R5. In fact, we don't really, have any meaning. There's no possible meaning for the angle between vectors in R5 because angles are in physical space. So it's sort of meaningless to even think about what we mean by the angle between vectors in R5, and we wouldn't do that. But what we can do is use this formula, which was developed in R3 or maybe R2, in R3 or R2, and we can just say, oh, all of these operations work whether the vectors are in R2, R3, or R10, or whatever. So we have a formula for the angle between vectors in any dimensional space. Now, as I said, it doesn't exactly make any sense to talk about angles, but we can just use this formula for what we mean by angles in R10 or R20 or whatever it is. So that's kind of cool. And I guess it's also cool because we can just given these two vectors just in R2, no, sorry, in R3, we can figure out the angle between them using this formula. So I guess it's handy in that sense. But it's kind of very interesting that you can extend this to any dimensions because these operations work with vectors from any dimension. So now we have a kind of extension of the idea of angle to vectors in any dimension. Okay, let's just look at this theorem once more. And let's assume, just for a moment, that A and B are non-zero. So suppose that both A and B are not zero. Okay, so if A and B are not zero, then the only time that the dot product can be zero is if this is equal to zero. And cosine of zero, cosine of theta equals zero means that they're perpendicular. So the only time that the dot product can be zero is if they're perpendicular. And furthermore, if they're perpendicular, then the dot product is equal to zero. So we can say if and only if, and that's what they state next. If A and B are non-zero, then if this equals zero, if the cosine of theta equals zero, which means they're perpendicular, then A dot B equals zero. And if A dot B equals zero, then they are perpendicular if they're non-zero. If either A and B are zero, then we can't really even talk about the angle between them. Okay, so they say that A and B are called perpendicular if A dot B equals zero. So why do we have to say it that way? I mean, we already know what perpendicular means. Well, we're talking about what about if you have 10-dimensional vectors? We'll still call them perpendicular. Actually, we don't use the word perpendicular then. We use the word orthogonal. So if you're not talking about 2 or 3 dimensions, you usually use the word orthogonal, although sometimes it's convenient just to say perpendicular, but usually we try to use the word orthogonal instead of perpendicular, because perpendicular sort of is like for physical things, but orthogonal means, 5-dimensional, 10-dimensional, or whatever. We still talk about orthogonal, but basically it's an extension of the idea of perpendicular, extension beyond 3 dimensions. So then she says, if either A or B is a zero vector, we cannot use formula 4 because the angle theta is undefined. Nonetheless, since A dot B will still be equal to 0 in that case, because if one of them is 0, then the dot product will be 0. Or if A or B is 0, we adopt the standard convention and say that the 0 vector is perpendicular to every vector, because we just defined what we mean by perpendicular, and it was that A dot B equals 0. And of course, if either A or B is 0, then the dot product will be 0. So if we have a 0 vector, we'll still call it perpendicular to any other vector. So next they show an example where they say this is perpendicular or orthogonal to this, and because we take the dot product and we get 0. So now we have a test for when vectors are perpendicular. Actually, we have a kind of definition of when vectors are perpendicular. And again, this holds for higher dimensional vectors. Okay, next we want to talk about a very important idea of vector projections. Okay, so let's look at this picture down here. So we have two vectors, we have A and we have B. And by the vector projection, or the projection of B onto A, so you have to say you're projecting one, specifically one onto the other, not the other way around. Anyway, by the vector projection of B onto A, we mean, suppose we had a light up here and it's shining down, then what's the shadow cast by B into the directional vector where A is, or onto this plane, in other words. So we can, obviously it's clear that the shadow is here. So that is called the projection of B onto A. That's what we mean by the projection. So it's that shadow. From up above here, we shine down and we get the shadow. But it's not just I mean, it's a vector. So it's not just like a length, it's a vector. Okay, so it's the length, but in this direction. Okay, so it's in this direction. So that is what we mean by the projection. So they say given two non-zero vectors A and B, we are given two non-zero vectors A and B. By the way, A only went to here, but the projection can go further. It's the shadow in the direction of A, so to speak. Um, so given two non-zero vectors A and B, imagine dropping a perpendicular line. Okay, we drop a perpendicular line, or we get the shadow um, from the head of B to the line through A. So here. Then the projection of B onto A, and this is how it's denoted. So it's a little annoying. You have to figure out which is which, but this is the notation. The projection of B onto A is this. That's not what we mean by the projection of A onto B, which would be written like this, would be written like that. That's different. That's something along this direction. So you kind of you'd shine a light over here, and you'd look in this direction. So it would be like this here, something like that. Anyway, that's different than this. So, you have to learn the notation. So the projection of B onto A, that is this one down here, is written like this, and the projection of A onto B, that is this one over here, is written like this. So you just have to learn which is which. And notice that they do say that it's the vector represented by the arrow in this figure. Okay? So it is a vector. Not just the distance here, it's a vector. And here, we can still do the same thing. Here we have A, and here we have B. So you may say, well, how can we talk about that projection? In that case, still the same thing. You just have a light shining down, and it goes down here, and it's this. But again, it's not just the distance, it's the vector, that vector. Okay? Okay, so we have this idea of what we mean by projection, but we want to get a formula for it. So we want to say what we want a formula for the projection of B onto A. And the final answer is going to be down here, is going to be here. So this is the formula that we arrive at for the projection of B onto A. So let's just check out one thing about this formula first before we go back and look at where it comes from. And that is it really a vector? Because we kind of insisted that it should be a vector. So let's check that out. Is it really a vector? Okay, so let's think about just this part here first. Well, that's not a vector because that's a dot product, so that's a number. Okay, now let's think about this part. Well, that's not a vector because that's just a dot product, so that's a number. So what about this whole thing here? Well, that's not a vector because that's a number divided by a number, which is a number. Okay, so far in the red circle here, we have a number, but it's multiplied times a vector. So, of course, a number times a vector, we call that scalar multiplication, and that's a vector. That's just a multiple of A. So it's just like if A was this vector, then if we multiplied it by, say, 2, then it would be another vector, just double the length. So at least from this formula, we can say that at least it's definitely a vector. Okay, but of course that doesn't prove the formula. It just says that the formula is not obviously wrong. Okay, so we have to prove the formula, and actually I'm not going to prove it, although the proof is important, but I won't do it here. So we'll just scroll through it, and you can see that before they prove it, they state this proposition. In other words, we need this proposition to do the proof, or having this proposition makes the proof easier or more organized. So let's just see what it says, the proposition. So it says if we take the norm of k times a, So remember, A is a vector, K times A is still a vector, and so we can put that into the norm, and that will give us the length of K times A. And it turns out that you can do this. That is, you can take the absolute value of K, and remember that makes sense because K is just a number. You can take the absolute value of numbers, and then times the norm of A. So you can split this up like that. So, and they actually they don't prove that one, but then there's one more, and this is important. We do need to check out this concept. That is, what do we mean by the word a unit vector? So a unit vector is just a vector that has a length of 1. So it can be in any direction, but it has a length of 1. That's what they mean by a unit vector. So they say in number 2, they say a unit vector, i.e. a vector of length 1, in the direction of a non-zero vector A is given by this. Okay, so if you have A, so remember A is some vector, and it points in some direction. But this doesn't have to be a unit vector. It could be any length vector. But if you want to get a unit vector in the direction of A, for example, suppose that orange one has length 1 and it's still in the direction of A, so we'd call it the unit vector in the direction of A. So if you want that, how do you get it? Well, they say all you have to do is take A and divide it by something, which that makes sense, right? Because we just want to scale A, right? I want to take A, but I want to keep in the direction of A, but I want to multiply it by a scalar, some number, could be a fraction, but some number, and that will just change the length either this way, or maybe make it shorter, or maybe even make it point in the opposite direction, but we don't want to do that. But we can just multiply it by a scalar. So multiplying is the same idea as dividing. You just divide by the inverse. So we can say we want to take A and scale it by some amount. And then how much is it that we want to scale it by? Well, we want to scale it by the norm of A. Remember, the norm of A is the length of A. So this is just a number, a scalar. This is just a number. We're taking A and what we're doing is we're multiplying it, A, by this, by 1 over that. So we're multiplying A by that, and that's going to scale it to the right length. And it's easy to show that because all I want to do, I mean, it's obvious that this is pointing in the same direction as A because it's just a multiple of A. So I don't have to show that. That's obvious, and we've stated that before. It could be pointing in the opposite direction, but basically it's along the same line, so to speak. And then, but we have to show that it's of length 1. So what does that mean? Well, it means we have to take, so this is the whole thing that we want to show its length is 1. Well, how do we do that? We just check its length, which means we get the norm of this. Okay, but now we can use this thing, number 1. How do we use that? Well, this thing here is a scalar. It's a k, some k. And what did we say we could do with k? We could bring it outside of these double bars here, right? We can bring it outside. So we do that. We take this and we write it like this, and then we can bring this outside. But then we get this, and this is clearly 1. So this, that is the norm of the thing inside, is 1. That means it's of unit length. So this clearly, because it's just a multiple of A, points in the right direction, and now we've shown that its length is 1, so it's a unit vector in the direction of A, which is what we wanted to say. That what is the unit vector in the direction of A? You just take A and divide it by its norm. Okay, and then as I said, there's this proof here, and I will let you peruse that and get to this point here. So this is the formula. It's a little hard to remember it, uh, but this is the formula for what? For the projection of B onto A. So again, it's going to be a vector in the direction of A, and we need to know also the length of it. So we need to scale A by the length. So we're going to have A and then something else, which is a scalar, and that is going to give you the projection of B onto A. Remember, it's in the direction of A, not in the direction of B. If we want the one in the direction of B, we'd be asking what's the projection of A onto B. So this would be A, and this would be B, but that's not what we're asking. So she says it's not difficult to remember, but I'm not sure about that. Now, actually, I highly recommend that you view this video. He does a very nice job of explaining vector projections. And this is Vic Math Vector Projections. So it's only, well, it's 15 minutes, but I highly recommend that you watch it. Okay, this section, we're not going to cover this, the cross product. I don't think we need that. In this section, they also cover matrices and determinants of matrices. Maybe we'll talk about that later, but we don't need it right now. And then at the end of this section, they have a kind of summary of products involving vectors. So, we have, this is a kind of a product that involves the vector A. So we're taking a scalar times A, and there are some properties of that. And we just talked the last property. We just talked about this property just a minute or two ago, but there are other properties that we've talked about. And then they have products, dot product of vectors, and properties related to that. And then they have properties related to the cross product, but we didn't discuss the cross product. Okay, we want to go a little bit further in this chapter, and we want to talk about equations for planes and distance problems. So really, we've already talked about equations for planes, but we want to do it now with some vector notions. So they say we're going to use vectors. And then we're also going to solve some distance problems involving flat objects. So I guess that means kind of non-curved objects. So lines and planes. Lines mean straight lines. Planes are sort of not curved. And I guess we can say points are not curved. Although honestly, I've never seen that said like that before. Okay, so first of all, they're going to use this symbol to stand for some plane. So here's a plane, and they're using this symbol. And why are they using that symbol? Well, this is a Greek pi, and pi is actually a Greek p. If you want to spell something that begins with a p in Greek, you'd put this letter first. You might put like like alpha next. Like one way to write alpha is like that, right? So this would be PA in Greek. So anyway, this letter is pi, but it's a Greek P. So that's why they're using, calling a plane, they're denoting it by pi because it's a P, P for plane, some plane P. So, okay. So a plane pi in R3 can be uniquely determined by the following geometric information. So, one thing we might say is, if we know 3 points, then we can say there's only one plane that goes through those 3 points. So that's one way to uniquely determine a plane, but that's not the way they're going to do it here. So what they're going to say is, looking at this picture, they're going to say that suppose you have a vector n. Now this vector n, the way they've drawn it, they're trying to say that it's not in the plane. In fact, what they're saying is that this is supposed to be perpendicular to the plane. So in other words, suppose we have a vector n, then we can talk about the plane which is perpendicular to n. But you'll say, no, 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 that's not right, because there are many planes that are perpendicular to n, and that's right. But at least it's not all possible planes that are perpendicular to n, right? There are many planes that are perpendicular to n, but there's certainly many planes that are not perpendicular to n. So we're going to put in one condition, is that the plane has to be perpendicular to n, but that doesn't single out a unique plane. But among all the planes that are perpendicular to n, we can talk about the plane which is perpendicular to n and then goes through a particular point. And once we say that, once we specify a particular point, then there's only one plane that will satisfy both of those conditions. That is, there's only one plane that will be perpendicular to n and contain some given point, which they denote by p0. Okay? So we can specify a plane in this way. Instead of doing it in terms of 3 dots in the plane, we can say we want the plane which is perpendicular to some given vector n and goes through some given point p sub 0. So that's what they say. A plane P in R3 is determined uniquely by the following geometric information. A particular point in the plane and a particular vector n that is normal or perpendicular. So we talked about the word normal, perpendicular, and normal just means perpendicular. And so once we specify the vector, we're given some vector and some point, then there's only one plane that will satisfy those two conditions. Okay, now the next sentence is interesting. Okay, so what do they say? In other words, pi, this plane, it's a set of points, right? A plane is a set of points. It's an infinite set of points. But it's not every point in 3 space. It's just a very limited set of points, even though it's infinite. Okay? But it is a set of points. So they say, in other words, pi is the set of points, and here we give them kind of arbitrary coordinates, x, y, and z, in space. Now here's the interesting statement, such that a vector from p0 to that point P, so every point in the plane, here's a point in the plane, any point in the plane, if we start with a if we start here and draw a vector to that point, what can we say has to be true? That the angle between the normal and this vector has to be 0. Sorry, not the angle between this vector and this vector has to be 90 degrees. So, in other words, n will be normal to this vector p0p for any point in the plane. So if this is a point in the plane, if I draw it from p0 to p, that vector has to be normal to n, and any other point in the plane has to have that same property. That if I start at p0 and go to another point in the plane, I'll get a vector, and that vector also has to be perpendicular to n. And if there's a point that's not in the plane, for example here, and if I construct this vector, that won't be these won't be perpendicular, n and this vector here. So all of the points who, when you construct their vectors starting at p0 and going to that point, when the angle between that and the normal vector is 90 degrees, or when this vector is normal to this vector, then all of those points, the collection of all of those points, is exactly the set of points we mean by the points in the plane. So now, remember, this is like non-specified, this p, just like this point P was non-specified. We didn't say it was x0, y0, z0. This means that the plane pi is defined by the vector equation. So this is a vector equation. N dot this vector where this thing is not specified. So any point that satisfies this will be in the plane. So this is a specification of which points lie in the plane. So this, we can say this is the vector equation for the plane that we want. Remember, the dot product equals 0 means that the angle is 90 degrees between n and this vector. So what did they say in the first sentence here? They said, in this section we use vectors to derive descriptions of planes in R3. Well, that's what we've done. We now have a kind of a description, or actually a specification of what we mean by the plane perpendicular to n containing the point P0. Okay, now don't forget we mean that P has the coordinates x, y, and z, and they're not specified. It's not like x0, y0, z0. But P0 is specified, so that has specific coordinates, which we've called x0, y0, and z0. So the vector going from P0 to P is, and we've seen this before, it's this coordinate minus the corresponding P0 coordinate, that is x minus x0, y minus the corresponding y0 coordinate, I'm sorry, P0, the y coordinate of P0, which is y minus y0, and z minus the corresponding z coordinate of P0, which is z minus z0, and times I, j, and k. So that's this vector, that's this vector. So this equation is that dot n. Well, n, we didn't point it out, but n, they said a particular vector n with, has this as the first coordinate, this as the second coordinate, this is the third coordinate. So given that that's our n, then when we multiply that times what we just said here, which is what we're doing, that times this, then we get this dot this has to be equal to 0. So we just kind of expanded this equation. So now when we write this out, and we expand this, remember this is a dot product, so it means we have to take this times this, and this times this, and this times this. And that's what we do here. And we get that that equals 0. Now this looks much more like the equation for a plane. In fact, when we simplify this, and we have a bunch of constants which we end up calling d, and we just get ax, by, cz, and then the other things, this times that, and this times that, and this times that. We just combine that into a d, so we get something like this. And that looks much more like the equation of a plane, or it does look like the equation of a plane. So we were on the right track when we wrote this, because this generated this. Okay, so now we can do something. We can do this example. So suppose we want the equation of a plane through this point with this normal vector. What does that mean? This vector should be normal to the plane. So we can use this to get the equation. In fact, this is the equation. So we just put in n and this. So we need the n and we need this. So here's they said here's n. So here's n. And then this gives us this. Right? Because we have to take x minus the 3, y minus the 2, and z minus the 1, and that gives us what we need. So this is the equation for the plane in example 1. But we can expand this, just like we did the expanding before, and we get this, and then we get this. This looks more like the equation for a plane, but it's the same as this, actually. So either way of writing it is fine. So I say not only does a plane in R3 have the equation uh, of the form given by 2, in other words, given by this, but anything given by this will be a plane, or given by this will be a plane. So this can be called the general form for the equation of a plane, but so can this. But this is the vector form of it. Okay, now they do some. Now they it's a different question. They give you the equation for the plane, and they want you to find a normal vector to the plane, and also identify points that lie on the plane. Okay, now going back to this example here, if you look at the normal vector and you look at the result, it can't be a coincidence that the normal vector has 2, -1, and 4, and this is 2, -1, and 4. So we're not proving that yet, but we can see that we can get a normal vector just by reading the coefficients of x, y, and z. So therefore, with that understanding, we can say that this 7, 2, -3 will be a normal vector to this plane. So they say a possible normal vector is 7i plus 2j plus -3k, or -3k. However, any non-scalar multiple of n will do just as well. So we could multiply this whole equation by a scalar, and that will give us another normal vector. Then finding points in the plane is simple. You can just arbitrarily set y and z equal to 0 and solve for x. So that will give you 1 point, and then you can do other things similar to find the other points, other points in the plane. Okay, you can read this as kind of a cute little problem, and you can also read this, but I won't go through either of these. You can continue to read this, and so on. Okay, we could also do this, but I'm going to try and avoid it right now. Parametric equations of planes. So we've talked about parametric equations of lines, but we can also do something similar for planes, but I'm going to try and avoid that if possible. Okay, in this example 7, they talk about the distance between a point and a line. So here's a line. We want to know the distance, and we can use the concepts that we have developed to get this. And you can go through it, and the answer turns out to be this. So it's here, but this could be positive or negative, but we take the magnitude of it. This is actually, I guess, the vector that connects these two, and then we take the magnitude of it, and we get the length. So you can go through this. This is a good example to check. And then we can also do something similar to get the distance between two parallel planes. So you can go through this, and also the distance between two skew lines. So here's a line, and here's a line, and we want the distance between those two lines. Okay, and then they talk about some n-dimensional geometry. So, this is like, we have geometry for R2 and R3, but we already talked about the fact that now we have a concept of an angle for vectors in Rn. And what other interesting things can we do generally in Rn? And we can sort of call it geometry in Rn. But anyway, first of all, we say, what do we mean by a vector in Rn? And of course, we know that. That's something like this. And then we get some important. First of all, we have the basis vectors in Rn. So remember, we had I, j, and k before. Those are called the standard basis vectors in R3. But if we have R4 or R5 or R6, what do we mean? Well, in the standard basis vectors in R3, it's 1, 0, 0. I'm not going to write the commas right now. The other one is, next one is 0, 1, 0. I didn't write the commas. And the last one is 0, 0, 1. So you can sort of see generalizing from this. If you had R4, you'd have 1, 0, 0, 0. I'm not writing the commas. And then you'd have next one is 1, I'm sorry, 0, 1, 0, 0. And then you'd go 0, 0, 1, 0, and so on. And so more generally, for Rn, you'd have 1, 0, 0, 0, then you have 0, 1, 0, 0, 0, 0, and you go all the way. You keep doing this until you put the 1 at the end, and those would be what are called the standard basis vectors for Rn. Okay, and this is just a generalization of the idea of the I, j, and k basis vectors in R3. And just like before, we could write A in terms of the standard basis vectors in R2 or R3. Now, with this idea of the standard basis vectors for Rn, if A is in Rn, we can use the same thing to write A in terms of the standard basis vectors, just like we wrote it in terms of I, j, and k. Now we can do it in terms of E1, E2, E dot, 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 dot. And all you're doing is this times this gives you what? Gives you A1, 0, 0, 0, 0. And then you'll do A2 times this, and that will give you 0, A2, 0, 0. And that's what we're doing. Okay, so you can split this up in terms of these standard basis vectors. You can write it like this. Okay, and then there's something called the Cauchy-Schwarz inequality, which is an important thing, but we're not going to go through the proof of that. But just you can see here, it's something about dot products, but let's not go through that now. And you can go through the proof of that. And then there's something called the triangle inequality. So what is that? If you have A here and B here, what is A plus B? Well, we know what A plus B is. It's there, which is like the hypotenuse. It's also the length of this thing, right? It's the hypotenuse. But anyway, it's here. These actually, I drew this so that these are right angles, but they don't have to be right angles actually. So anyway, so here we have A and B, and here's A plus B, and this is all in 2 dimensions. All this thing is saying is that if we take the length of the orange one, which means the length of A plus B, it's going to be less than the length of A plus the length of B. So I think everybody knows that. But this is true not just in 2 dimensions, but it's actually true in Rn. So this is kind of a generalization of this idea that we all know about. And it's called the triangle inequality because in 2 dimensions, it's easy to see because it's talking about a triangle, but in n dimensions. Okay, so now we are going to look at this chapter, and we're going to jump right to here, and we're not going to follow the full approach that they use in this text. We're just going to review some of the ideas that hopefully you're already familiar with. So they give the definition of derivative. This is just the standard function from R to R, so it's just a very simple function with just one input and one output. And then they go through a kind of slightly different way of defining partial derivatives, but I'm not going to go through any of that. I'm just going to assume that you have seen it before, but I will just review what it looks like. So here we have a function of two variables, unlike the previous situation. And so in effect we have three variables because we have the output variable as, for example, z, and then we have these input variables. So this is a picture of maybe what this function looks like, maybe. If I try and plot this in Google, it doesn't really look anything like that. Maybe I didn't type it properly, but anyway, we won't worry about that. We'll just assume that it looks like this. And then the question is, what is the partial derivative? And we can, as you probably know, we just treat y as a constant because we're asking for the partial derivative with respect to x. So we get this result, and if we do the partial derivative, okay, and another example, if you have g as this function, you can calculate that this is just a different notation for the partial derivative of g with respect to x, the partial derivative of g with respect to y. Okay, and then this notation just means that after you calculate the derivative, you put in the values for x and y. Okay, so now here's a function that has many input variables and just one output variable. So an example might be, just like we've been looking at, so here we have n different variables here. They happen to be all squared. So we have a function of these n variables, and then we have an output variable, which they're just denoting by x sub n plus 1. We might call it like y, or we might have called it z, but here they're just calling it x sub n plus 1. But just so you don't get confused, it's like z equals x1 squared plus x2 squared, and so on. So we have n different input variables. So we could ask for the partial derivative of z with respect to x1, the partial derivative of z with respect to x2, and we could just keep going until we got to the partial derivative with respect to xn. So that's exactly what we were just talking about a few minutes ago. So to keep things just a little bit more organized, we can write that as, let's say that function was called f. So going back to here, the function here, which is the output variable is z, but we can call the function like that if we want. So instead of saying the partial with respect to partial of z, z with respect to x1, z with respect to x2, we can say the partial of f with respect to x1, the partial of f with respect to x2, and so on. And we're just going to put them in like, kind of an organized way here. So we put the first one and the second one and put brackets around them like this. And actually this forms a vector. And, it has n pieces. So it's a vector in kind of n dimensions. But this vector is not, the elements of this vector are not numbers per se. So I wouldn't want to say it's a vector in Rn, because that would mean that we're talking about, n elements, but each element should be a real number in order to say, and that's what we usually talk about. So each number is like, each element is like a number, so we might have like 3 and 2 and 9 and so on. That would be a vector in Rn if there were n pieces here. But when we say Rn, it means this R stands for real numbers. So it means that each of these entries should be a real number. But that's not the case here. Actually, we saw that each of these is like a function. Let's just go back and check that. So here, the partial of f with respect to the first input variable, that would be like x1 in the notation we were just looking at. But here we're calling it x and y. So instead of x1 and x2, we're calling it x and y. But anyway, the partial of f with respect to the first variable, it's not a number. This is not a number. This is a function. So I don't want to say that the result, when we put these together, like put this one in here and this one in here, I can't really say that's in Rn because if these are not numbers in here, this is not a number, this is not a number. So, but it is still, this is a two-dimensional object. I can say that. I just don't want to say it's in R, and I don't want to say it's in R2. Because R2, as I just said, implies that these are numbers in here. They're not. They're functions. So we just don't want to say that. Okay, so going back to this, we have the partial of f with respect to x1 and x2 and x so on up to xn. And so this is just like an organized way of writing all the partial derivatives for like this function. We have partial derivative with respect to x1 and the partial derivative of this whole thing with respect to x2 and so on. So we have all of those partial derivatives that we can think about, and we just want to put them in like an organized list. So we do this, we put them in this organized list, but then we can recognize, oh, that list, we can think of it as a vector itself, which is maybe a nice thing to think about. But anyway, this is just a list of all the partial derivatives, and we give it a name, and it's this. Now, just one more thing. Why is this x bold? Because that's to tell us that the input into f is not just one element, but there are many. It's got x1, x2, x2. So x, that bold x, is so it's got x1, x2. So that's why, right? We have many inputs into our function, and so we can express that as saying it's a function of many inputs. A nice quick way to write that is that it's a function of the vector x, and this is the vector x. So this is just a nice handy list, and we call this list this thing, and we read this thing as the gradient of f. So the gradient of f is just all the partial derivatives put into a handy list, which actually is a vector. So we just want to have this definition. And just like we might ask if we have the partial of f with respect to x, and then we say, what is that at a particular xy pair? We put in the 0, for example, and the 0, and we get out some result when we evaluate it at a specific point. So in the same way, with this gradient, we can say, well, what is it when we put in a particular value of x, and when we say a particular value of x1, x2, x3, x4, we're saying a particular value for the vector x. So we're filling in all of these things, and we get a particular one. For example, we might say when x1 is a1, sorry about that, when x2 is a2, where a1, a2 are particular numbers, and a and so on, up to the end. So, and then we'll call that a, because, this might naturally be called a. So we want to know what's this evaluate to when we put in a particular set of values a, and then of course we put in the particular set of values into each of these pieces. So this is the gradient, and this is which is a vector, And this is the gradient evaluated at a particular point in the n space. Okay, and then they have another definition to make things a little more complicated. This is really enough actually, but we can also have the same thing here that we have here. We just have here, we have round brackets around it, and here we have square brackets, and we don't have we have commas here, but we don't have commas here. So except for that, it's the same thing on the right-hand side here and here. Now, when we have commas, that means we're talking about a vector, or at least in her book. And when we have just spaces, that means we're talking about a matrix. So, who cares, right? It doesn't matter, whether we think whether we call it this a vector or a matrix. But in some minor sense, it's important, um, just a kind of bookkeeping sense. But anyway, so um, this is the same stuff as written here. It's just that here we have commas and here we don't. And here we have open bracket or round brackets and here we have square brackets. So except for that, it's the same stuff. And when we write it like this, she means to say that it's a vector. And when she writes it like this, she means to say this is a matrix. So that's the only difference here. And then the name, though, in this case, when we think of it as a vector, is called the gradient. And when we think of it here, it's called the derivative. So what are we going to do about that? We'll just accept her notation. And maybe this notation is somewhat standard, so it might be worth noting it. So let's figure out the gradient for this example. So what we really need to do is take the partial derivative of this thing with respect to x1, with respect to x2, and so on with respect to x3, and all the way up to xn. Well, that's pretty easy, because when you take the partial derivative of this whole thing with respect to x1, all this stuff is just treated like a constant, and so that's just 0, and you just get 2x1. And if you take the partial derivative of this thing, call it f or call it z, whatever you want, if you take the partial derivative of that with respect to x2, then this is 0, and all this stuff is 0, and then we just get 2x sub 2. And you can see the pattern here. You get 2x sub 1, you get 2x sub 2, get 2x sub 3, and so on up to 2x sub n. And so they write 2x sub I for the partial of f with respect to x sub I. So now we have this, we have this, we have all of them. So we can just dump them in here, and that's going to be our gradient. So let's do that. So it's 2x1 comma 2x2 all the way up to 2xn. And that is called the gradient of this function. We call this function f, or I guess we can call it z, and that is the gradient of, let's say, f. So here it is. And so it's a vector of all the partial derivatives. Okay, and this is the notation for it. So this is called the gradient of f, and this symbol is called nabla. Nabla. So we could say, well, what's the gradient of f at a particular point in this n space, right? We're talking about n space, and so we can say, oh, well, what about when, n space, we have x sub 1, x sub 2, x sub n. So we could say like when x is 2, and I'm sorry, x1 is 2, and I'm sorry, and x2 is 7, that's supposed to be a 7, and x3 is 8, and all the way up to xn is like 4, something like that. So we could say, well, what is the gradient at this point? Because the gradient looks like this. We can ask, what is it when we put in this into x1 and 7 into x2 and 8 into the next one, and what did I say, 4, into the last one. We can say, well, what is that? So we can say, let's evaluate the gradient at this particular point. And here in this example, they evaluate this gradient at this point. Okay, so you just put in these values into here and you get something out. Well, I guess this is what you get out. You get 2 times 1 is 1. I'm sorry, 2 times 1 is 2. And this one is 2 times 2 is 4. And the last one is 2 times n. So you get something like this out. And then if you want, you can say what's the derivative of f at this so-called point. And then you put this point or this point into here. I'm sorry, the into the same thing basically, but you don't have the commas and you put square brackets around it. And that's called the derivative, and that's just the matrix form, and this is just the vector form, which is hardly different at all. You know, like I said, the only difference is here you have commas, and here you don't, and here you have round brackets, and here you have squares, so it's really not any different, or it's only slightly different. Okay, so the next topic that we want to discuss in this book is in section 2.6. It's called the directional derivatives. So they say that we've already talked about this, the partial derivative of f with respect to x, and we've also talked about the partial derivative of f with respect to y. And again, this just means that once you figure out the derivative, then you can put in values for x and y into that derivative. And we're putting in, for example, a and b. And they're illustrating what the derivative is in this picture. So here we have some function, some z equals f of x, so it's some surface. And we're trying to take the derivative of z with respect to x. So the partial of z, or partial of f, with respect to x. And we've said that, in class at least, we said that means that basically you're slicing this surface. We're fixing y. That's what we mean when we take the derivative with respect to x. So we're fixing y, and fixing y means we're making a plane, and we're cutting the surface with that plane. And so we get this kind of curve, and then we're just talking about the derivative of that curve, and that's just the standard simple derivative. So that's just the standard derivative in basically, in like a plane. So in a plane, we have a curve, and we talk about derivatives, and that's the first semester derivatives that we learn about. So that's how we sort of simplify the derivative of a whole. When we're talking about surfaces, we just reduce them to the regular derivatives, and by slicing them with a plane. So here what they do is they draw in the I vector that we've talked about. So that's just a unit vector in the x direction, and it's one of the standard basis vectors. The other ones are usually called j and k, but we talked about even in a higher dimension what we can call them. But anyway, in just 3 dimensions we have I, j, and k, and this is one of them. This is the I one, and they've just drawn it in there. So now we're going to call this the derivative in the I direction. It's the same thing, we're just going to call it the derivative in the I direction. And then we could also, of course, do the same thing for the derivative in the y direction, or the j direction. But now the next thing we want to do is think about, well, what about if we wanted to consider the derivative in some other direction? So not, when we do the partial derivative with respect to x, we're doing the derivative in the I direction. When we do the partial derivative with respect to y, we're doing the derivative in the y direction. But suppose we wanted to do it in some other direction. So that's what we want to think about now. And this is a picture of that. So I guess we have the same surface here as we had here, but here we're saying, well, what would be the derivative in this direction? So it's not the x direction, not the I direction, and not the j direction, but some other direction. And of course, the most convenient way for us to identify a direction is by a vector. So that's what they did here. They put a vector v to indicate some other direction that we might be interested in finding the derivative in that direction. So that leads us to the idea of what they call the directional derivative. So here they say the vector v, and could be, we can give it some coordinates, just like we do with all vectors. And we can also write it this way, just like we can do with any vectors. When we write it this way, we can alternatively write it this way. And visually, we could sort of draw a plane in that direction and imagine that it cuts the surface. And so that's going to generate some kind of curve. And so we're asking the derivative of that curve, and that's the curve that's dictated by the direction of v. I'm sorry, yeah. And the plane, this shaded gray plane, is dictated by the v vector. So we didn't really go through all the details in the book, so this sort of doesn't make a lot of sense to us. So I don't want to focus on it. But if you wanted to go through all the details of the book, then this would make sense to us, to you. But anyway, they said, suppose we have this function, and we have a direction, v, that we want to find the derivative in that direction. And of course, the v has some coordinates like this. It can be expressed like this. Now, it's important to notice that v is an element of R2. So what does that mean? So we're thinking about this whole space. This whole space is R3, but where is V? V is in the plane, the bottom plane there, the flat plane, the XY plane. So it's important to notice that V is an element of R2. It's not an element of R3. And it turns out by doing a little of this, this is like the original definition of what we mean by derivative, and they've handled this direction now, and they end up with this. Now, we don't want to justify this, but this would be the direction in, I'm sorry, the derivative in this direction. Okay, so there's a great theorem here. So this is if we want to know the derivative in the v direction. So that's what this means. We had before the derivative in the x direction, the derivative in the y direction, but now we want the derivative in the v direction. And this is a great result, which we're not going to try and prove it, but it says that all you have to do is take the original gradient and then do the dot product of that with the v vector to get the derivative in the v direction. Remember, this is not in the v direction. Remember what this is. It's the partial in the x direction, comma, the partial in the y direction, if we're only talking about x and y as the input variables. If we're talking about more input variables, then it's going to be a longer string. Remember, this is actually a vector itself. And then you take that and you dot it with v. Now, first of all, let's just say, does this make any sense? I mean, can we do a dot product of this with this? Well, we'd better have a vector on this side, and we'd better have a vector on this side. Obviously, we have a vector v, but is this a vector? Yeah, we said that many times already. We said that this is a vector. And maybe in this case, it's just a vector. Well, no, it's especially an n-dimensional vector. So, okay. So it's a vector, and v is also a vector. So we can dot them. Hopefully they both have the same number of elements. Otherwise, we can't dot them, but they do have the same number of elements, this one and this one. So we can form the dot product. And that is going to give us the what we're asking for here. Now we don't have any intuition of where this result comes from. We're not discussing it. So you can go back and look at this, but it really involves sort of looking at a lot more than just this previous section. You have to go through many other sections together to have all of this make sense. But anyway, this is a wonderful result. We want the derivative in some v direction. All we have to do is get the gradient and dot it with that v direction. So let's take a look at this, see what they're talking about. So suppose we have this function, which is a function of x and y. And I guess we considered this before. And by theorem 6.2, this one here, uh, applies to tell us that if we want for any unit vector, so for any v should be a unit vector. For any unit vector, suppose we want the derivative in the v direction at 0, 0, at the origin. Note that we can ask for the derivative in the v direction, but we have to also say at what place in the v direction, at what point in the v direction. In other words, here we're asking at the v direction, but it's at the point apparently a comma b, right? We're going out a in this direction, or maybe it's here, a in this direction, and then b in the y direction, so we get to here. So we say at this point in the v direction, but we can ask at any point in the v direction. We could say, let's go from just this far in the x direction and just this far in the y direction, so we're like right about here. We can still move in the v direction. So we have to say at which point in the v direction and the v direction. We have to say in the v direction. So we also have to state the point. So here, just to make the problem easy, they're going to use the point 0, 0, because that's going to have zeros in it, and so it's going to make the calculations easier. So here they say the derivative in the v direction at the point 0, 0. So what does that mean? We're going to have to calculate, we're going to use this theorem, so we're going to have to calculate we're going to have to provide the derivative, the gradient, which is going to be a vector, and then we're going to plug in the point A, but we're going to plug in the point A is 0, 0, so we're going to plug in 0, 0 into our gradient, because remember the gradient is a pair of partial derivatives. In this case, it's just a pair because it's just in the x and in the y directions. Generally speaking, it looks like this, but we're only doing it in the two directions because we're only considering something in R2. That is, our vector v is only in R2. That is, our input variables are only in R2. So we only have two partial derivatives that we have to calculate, but we have to calculate them. So here's our f function, and we have to calculate the two partial derivatives. So we have to calculate what's the derivative in the x direction, so we have to keep the y fixed and calculate the derivative. And for example, that's going to be what? 2x minus 3y plus 2, right? So that's a function of x and y. So then we're going to put in the values 0, 0 into x and y, and we're going to get something out, and apparently this is what we get. And then we're going to do the same thing for the partial derivative with respect to y. We're going to calculate the partial derivative with respect to y to this. That's going to give us something in x and y. And then we're going to put in 0, 0 into that, and then I guess we're going to get this, minus 5. And then we have to dot that with this part here. That is, we have to dot that with our v, and we're saying that v is this. We're being a little bit general about our v. And so finally we get a kind of a little bit general answer of what the directional derivative at 0, 0 is in terms of v. And here we let v just be general, so we could plug in some particular direction defined by a particular v and w, and then we plug that in, and we would get actually a actual derivative in a particular direction starting at 0, 0. Do they have a picture? No, they don't have a picture. But anyway, if we want the derivative in the v direction, and we're standing at the origin, and we want to point in the v direction, I'm saying standing at the origin because they're saying at 0, 0. So what do we have to do? We have to take the gradient at 0, 0, and then dot that with this v. So what does that mean? So the gradient, remember we wrote it as a vector, but remember that any vector, we can always rewrite it using I and j, and just putting these things in front of the I and the j, and that's what they've done, but they're doing it specifically at 0, 0. So they're saying that this part here means the partial means this, but they want to do it specifically at 0, 0, so they're just saying that here. They want to do it specifically at 0, 0, and also they want to do this one specifically at 0, 0, and then we want to dot that with this. So what does that mean? So that means you get, well, before they do that, they calculate what is this and what is this. So what is the partial of f with respect to x? So we can see what is it. It's 2x minus 3y plus 2. So that's what it is. And then we have to put in 0, 0 into that. So I'm not going to do that. But apparently we get 2i minus, this one becomes 5j. So suppose that's true. Then we have this is this, and then we still have this as this, and then we dot product them, and we get 2v minus 5w. And so that is the result, but this doesn't, not quite satisfying, like what is this? But we didn't say what specific direction we want. We're being general here, so we have to get a general answer here. But if we say, oh, I want to go in specifically the direction of 1 and 1, now that's not a unit vector, so maybe we can't do that. But anyway, you would put in, I guess you'd have to consider this and this so that you get a unit vector. But anyway, you just put in the v and the w that you want it, the direction that you want to go into here, and you'd get out a number. And that would be the derivative in that direction. So you get out some number here, and that would be the derivative in that particular direction when we're standing at the origin. Because we put. Okay, so now we have a way of calculating the derivative in any direction. So that's a very powerful theorem, and it was very simple. We just did the gradient dot product with the direction that we want to move in. And the direction vector should be a unit vector to make that work. So the next question is, what direction provides the greatest ascent or greatest descent? So in which direction is the the surface increasing fastest or decreasing fastest? So we know that there are some directions that we can move in, say in this picture here, some directions that we can move in where the curve doesn't even increase at all. Maybe, for example, this could be like in the y direction. Maybe the curve doesn't even increase at all. We don't ascend at all. We don't get any higher or any lower. I can't tell with this picture whether that's actually true or not, but it sort of looks like it might be true. So it might be if we move in this direction, we don't change our height at all when we start at this point. If we just move a little bit in this direction. Maybe that's not quite true, but anyway, there are other directions where we can move, for example, maybe in this I direction or some other direction, where we can get much more of a change in the height of the surface. So the question is, in which direction can we get the most change? Because remember, we're kind of doing this because the surface is an error curve, so we want to decrease the error as much as possible when we move. When we change our weights, we want to get as much of a reaction in terms of the error as possible. We want it to decrease as much as possible. So anyway, we're interested in what direction we can move in that will cause the greatest descent or the greatest ascent. So before we answer that, let's just check again. What is the gradient? And this is the gradient. It's a vector of partial derivatives. So I just want to point out that we can write the following. So we can write this: the gradient evaluated at a particular point. In fact, we just did that. We did the gradient evaluated at the point 0, 0, at the origin, in other words. But anyway, we can write the gradient evaluated at a particular point. For example, suppose this is our function, x squared plus y squared x. So that's f or z. And suppose we want the gradient, then we just have to calculate. We only have two inputs here, so we only have to calculate the partial of f with respect to the first and the second. So with respect to x, that's 2x y squared. Let's just write that down. And then the other part is the derivative of with respect to y, which is just x. Sorry, it's x to y. So now, like we did before, we can put in any point in here into here. In other words, if I want to put in, we did the origin, we put in the origin. So what did that mean? That meant we would put in 0 for x and 0 for y. So we do that and we get out a particular ordered pair, like we might, if we put in 0, what do we get? We get 0 and we get 0. So, but that's kind of a strange example, but you know, we could also put in, say, 1, 1, or 1, 2, or anything. So we could put in 1, 1, 1, 1. So then we get 2 plus 1. So that would be 3, comma, and then we get 1 for over here, sorry, and we get 2. So we get 3, 2. So the point is that we can put in any a into here, any point we want. For example, 0, 0, or 1, 1, or whatever we can put into here, into the gradient. And we're going to get out a pair, like 3, 2, or 0, 0, or anything else. So that is what we can do with the gradient. Now, going back to our question, the question we want to ask is, in what direction is the ascent greatest, or conversely, least? Or as they write it here, in what direction is the gradient or the directional, or as they write it here, in what direction is the directional derivative maximized? And the very interesting answer is that it is it is maximized when u points, so when the u vector points in the same direction as the gradient at the particular point that we're talking about. Remember, when we put in a particular point, we get out something like we got this out. So that's a specific direction. That's a particular direction. Could be this direction, could be some other direction, but 3, 2, or whatever we got is some particular direction. And that will be the direction in which the directional derivative is maximal, is largest. And that's what we wanted to know. So it's just the direction of the gradient. When we fill in a particular point, we get a particular gradient. And that stands for a direction. So the gradient tells us the direction of maximal change. So if we're talking about the error function as the surface, and we want the error to decrease as much as possible, when we make a change, remember these would be the weights. When we make a change in the weights, we want the error to decrease as much as possible. It's the gradient that will tell us what direction to go to make the biggest change. Now, I was a little confused when I was thinking about directions when I first learned this, but the direction is given in the xy plane because once, we're at this point, it means we're up here, right? We can say when x and y, the inputs are here, then this is where we are. And then we're going to move to some other place on the surface, but really that means in the xy plane we've moved somewhere else. So if we want to know where to move, we can say in the xy plane, which direction should we move? Okay, so the directional vector that we're talking about is in only the xy plane, even though the whole curve is in 3 space. Now, if the gradient tells us to move in this direction to get the most change, then actually the direction that we would move to get the least amount of, the direction of steepest descent will be in this direction. So actually, I misspoke just a minute ago. We don't want to move in the direction of the gradient. If we want to decrease the error, we would want to move in the direction of the negative of the gradient, the opposite direction of the gradient. So they say it's minimized when you point in the opposite direction of the gradient. So that is a very powerful answer. Now, I'm not going to go through all of the details here, but they arrive at this statement here, which says that the directional derivative based on a particular u, so in a particular direction u, remember we're located at a point A, we're standing somewhere in other words, and we call that place A. So the directional derivative, they give this formula, and this is where that result comes from. That is where the result that says we should move in the direction of the gradient comes from. And why is that? This says, given a particular direction u, this is what you're going to get for the directional derivative. But if you look at this part here, this is the magnitude of u. But remember u, we said it's a unit vector. So the magnitude of a unit vector is just 1, so we can just get rid of this part, and we get this. So this says that the directional derivative for any direction u is just this part. Well, this doesn't even have u in it. So this is like just a constant, doesn't depend on u at all. But this has u in it because this is the angle between u and the gradient. So when is the cosine largest? When the angle is smallest, when the angle is 0. So that means we want the angle between u and the gradient to be 0. That means that u should point in the direction of the gradient. Okay, so it might be useful just to go through some kind of example just to see this. Now, the example is not going to be the kind of example that we're interested in where we're talking about the error function. It's something else. We're going to be talking about pressure function, so air pressure. So whereas in our examples we had a surface in 3 dimensions, so we had 2 input variables, but here it's a little different. We're going to have the pressure, so the air pressure, so the input variables are x, y, and z. So we're using all 3 dimensions, spatial dimensions for the input variables. So the output variable is not, not sort of visualizable, but nonetheless, we can say we have some output variable. I don't know what to call it since we're using x, y, and z. I guess we could call it u. So that's our output variable, and we have 3 input variables in this example. And this is the pressure function. And this is on some planet somewhere called Nil-Rabo. And they're saying the distance, the units here are in thousands of kilometers. So as you move, like at 0, 0, 0, maybe it's not air pressure. I'm not sure what it is, some kind of pressure. But maybe it's the pressure, the internal pressure. But anyway, at 0, 0, 0, the pressure is, we put in zeros here, and there's no pressure there. And then as we go to different locations, we change x, y, and z, we get different pressures out of this function. So we can say, okay, at this particular point, what is the pressure? We can just put that into here. We get out some pressure, some number. And then we can say, what's the rate of change of the pressure when we're standing at this point in 3 space and we move in a particular direction in 3 space. So what direction? 1 in the x direction, 1 in the y direction, and 1 in the z direction, or 1 in the I, k, and j directions. So then we're using the first theorem that we saw, which said that the directional derivative in this direction is going to be the gradient at this point. That's what this says, the gradient at this point dot u. That's what we said earlier. We said earlier that the directional derivative in a direction v is the gradient dot v. So that's all we're doing. So here it's the gradient dot u because we want to go in the direction of u. We want to know the directional derivative there in the direction of u. And so we can just figure this out and dot it with u. And so they do that and they get that. So that is in this direction. But we might also want to know, like, in which direction does the pressure increase most rapidly? And we also had the answer to that. It's in the direction of the derivative. I'm sorry, of the gradient. So here's the gradient at this particular point. So we have this. When we do that, I'm sorry, no, we have, sorry. So they're taking this, which is this, as you can see from this part here, and then they're dividing it by the magnitude of this. So why are they doing that? Why are they dividing it by this? Because they just want to get the direction with it. They want to have the direction as a unit vector. So you don't have to do that, but maybe it's more standard to do that. So this direction is true. This is the direction of greatest ascent, but we can also divide it by a constant. It's still pointing in the same direction, and that's what we're doing here. We're dividing it by a constant, and when we divide it by this particular constant, this is the magnitude of this, then we get a unit vector pointing in the direction of greatest ascent. And then further, they point out that the actual rate of increase in this maximum increase direction is the norm of the gradient. So it's this amount. This is how much increase we're getting as we move in the direction of the gradient. Okay, let's take a look at this question. It says calculate the normal vector to the line there. So this is a line. This is the equation of a line. So I don't know what it looks like, but it looks like something. So it's the equation of a line. So we want to know the normal vector to that line. By the normal vector, we mean the vector which is perpendicular to this line. So of course we know how to do that. One way to do that is to write y equals, solve this for y, then we get the slope, and then we know that we take 1 over the slope and the negative of that, and that's going to give us the slope of the perpendicular line. So that's basically what we're trying to do here. But we want to express it differently. We want to say we want to get the normal vector to this line. And it turns out that all you have to do is take the coefficients of the x and the y, and that will give you the normal vector. So in this case, I mean this here, 3 and 4. So that will be normal to, maybe I shouldn't use that color, so that will be normal to the to this line. It'll be, in other words, it'll be perpendicular to this line. Now, how can we prove that? So what we would need to get a vector which is parallel to our line, and then if we found that vector, then we could take the dot product of that vector with this, and if we get 0, then we've seen that that means that they're perpendicular. So let's see what about that. So how can we start with this line? Let's solve this equation for y. So I hope I've done that correctly here, and you can stop the video and make sure this is correct. So if this is true, then the slope is minus 3/4. So what does that mean? So that means, by the way, I just drew this line in here arbitrarily, so I don't know. This is probably not anywhere near the right line. But anyway, the slope of the line is minus 3/4. Okay, so let's figure out what the slope means here. So it's, if we go over 4, we go down 3. So if we go over 4, we go down 3. So we have that point. So we have that line. By the way, this line, I just drew that arbitrarily, which wasn't terrible, but it wasn't right either. So anyway, this is the line. So what is the vector which is parallel to this line? Well, any vector along here is parallel, and in particular, the vector which goes from here, to this point, is parallel. Now, what vector is that? That's for -3. This is a negative. That's a -3. So it's 4, -3 is the vector. So 4, -3. Okay, so that is the vector which is parallel to this line, and my claim is that when you take that, and if you take the coefficients of these and form a vector which is 3, 4, if you take the 4, -3, and you take the dot product of that with the 3, 4, which I got from here, those two will be perpendicular, so their dot product will be 0. And you can see that that's true because you take 3 times 4 plus 4 times -3, you get 0. So that shows that to get the normal to this line, you can just collect the coefficients and form the vector 3, 4, 3, 4. Now, do you think that was just a coincidence? No, it's not a coincidence, and it's generally, of course, it's generally true. So we should prove that it's true, but we'll just say that it's probably not a coincidence, and that it is generally true that you can do that to get the normal vector. Okay, so that's very interesting. And also, how about if you have not just a 2D um, situation like we have here, we have x and y, suppose we have a 3D situation. So this, remember, is a plane. But what does 5, 4, 2 give us? If we form a vector, just like we formed a vector 3, comma 4, what happens if we form a vector 5, comma 4, comma 2? What does that give us in relationship to this plane? Well, it turns out that that's going to be a vector which is normal to the plane. What does that mean, normal to the plane? Well, that's not exactly clear, but it's sort of intuitively clear, right? We can imagine, sort of a vector which is perpendicular to the plane. But really what that means is, or another way to think of that is that that this 5, 4, 2, which comes from here, 5, 4, 2, is perpendicular to any vector that lies in the plane. So if we have any vector in our plane, in this plane, and we can, what can we do? We can take the dot product of, if we know a vector in this plane, we can take the dot product of it with this, and they will be perpendicular, meaning what? That the dot product will be 0. So that's what we mean. But we can just call it normal to the plane. So if we collect these coefficients and form a vector, they will also be, they will form a normal, in this case to the plane. In this case, it was to the line, to the orange line. So we'll call this vector 4, comma negative 3, this one here. We're going to call that a direction vector for this line, for this gold line. So this is a direction vector for the gold line. I guess I need to put arrows on there. Okay, I made it a little thinner. So there's that's a direction vector for the gold line. So we'll use that terminology, a direction vector for the gold line. Okay, so next we say, what do we mean by a direction vector for this plane? So as I just said, basically what we mean is any vector which is in the plane will be called a direction vector for the plane. Okay, by direction vector we mean as opposed to the normal vector. So a direction vector is sort of in opposition to or opposed to the normal vector. That's what we mean by the direction vector. So in the plane it could be any vector in the plane. And on the line, it could be any vector on the line, I guess we could say. So how can we find a direction vector? How can we find a vector in the plane? So you can just pick any 2 points in the plane, and there's any 2 points that satisfy the equation of this plane, and then subtract their position vectors. So we talked about that before. We have a vector here, point here. Whoops. So we have a point here and a point here. We can construct the vectors that look like this. That's the position vector for that point. This is the position vector for that point. We can call them OP1 and OP2, or we could call them A and B. And if we subtract A minus B, we'll get C, which is here and goes from B to A, as we've discussed. So, and that's going to be a vector in the plane. So we can just, that's one way to get a vector in the plane. Just choose any 2 points and subtract them, subtract their position vectors, and that will give you a vector in the plane. So we can do that. We can take x equals 0 and y equals 0 and find out what z equals. So we get 0, 0, 5 is 1 point, and then we can take x equals 1 and y equals 0 and solve for z, and we get z equals 5 halves. So another point is here. So we have 2 points in the plane here and here. And then we can subtract their position vectors. P2 minus P1, we call those the position vectors here. I call them A and B. And so if we do that, we get what we call a direction vector. And this is it. If we subtract those two, that's what we get. So that's an example of a direction vector for this plane. Okay, and then once we have that, our claim was that we can still do this trick of taking the coefficients of the plane, or of the x, y, and z from the plane equation, so 5, 4, 2, and if we dot that with our position vector, or direction vector, sorry, with our direction vector, then that is going to be 0. In other words, that they're going to be perpendicular. In other words, this does give us a normal, doing this 5, 4, 2, does give us a normal vector to the plane. And if you try the dot product of this and this, it does turn out to be 0. And the point here is, I guess, that this is not a coincidence, right? It's very unlikely that, just this is the only time that it's going to work, that when you collect these coefficients, that they're going to give us the normal vector to this plane. So we can prove that it's true, but I just want to show you this as, I think this is sort of makes you believe it without actually proving it. So now we know a way to get the normal vector for a plane, but we don't actually need it for the plane for what we want to do. We just need it for the line. So we just need it for this case. So we have a line, we have the direction vector for a direction vector for the line, and then we collect the coordinates here, and we get a vector, and this vector and the direction vector will be their dot product. Well, those vectors will be normal to each other or perpendicular to each other, and the way we show that is just take their dot product, and it'll be 0. Okay, so now that we have some understanding of the gradient, we want to go to this problem. Now, this is from Khan Academy, and I can't do half or a quarter as well a job of explaining this as they do in these videos, so I definitely recommend that you take a look at these videos, but I'll just make some comments here. So here we have a task which is to maximize a function. And this function is clearly a function of 2 variables, and we can see the way it's constructed here. So it's x squared y. So we want to maximize it or minimize it depending on the task. Here they want to maximize it. And of course, in first semester calculus, we talk about the idea of maximizing or minimizing a function, and we also talked about it in the previous discussions when we said we wanted to find the minimum of the error function. But anyway, in first semester calculus, we do talk about this kind of problem. So, we might have some kind of curve like this blue one, and we want to find the lowest point, or the minimum. And we learn in that first semester calculus that we can use the derivative, because the derivative tells us the slope, and usually the slope will be 0 at the minimum, also at the maximum. So we can use that fact, so we can set the derivative equal to 0 and find all the points where the slope is 0, And that will certainly help us to find the minimum. Instead of having to look at every possible point, we only have a very small set of points here. There's just one point where the slope would be 0. So we can do something similar when we have two variables, and you don't cover that in the first semester of a calculus course, but you might cover it in like the third semester. And it does involve taking derivatives, but it involves in particular taking partial derivatives, because taking the regular derivative here sort of doesn't make sense. You have to talk about partial derivatives. But we can do something like that. And in fact, in the textbook that I've been following, they do cover how to do that. But here, if we look at this function and we ask what's the maximum, and if this might be the picture of this function, well, it looks like it goes up forever. So there is no maximum. Basically in the same way that in this function also there's no maximum. There's a minimum, but there's no maximum. Now I think of that other function, there's not even a minimum, but still in this function here, there's also no maximum. However, if we said, oh, well, we're only going to look between here and here, then we can talk about the maximum. Maybe the maximum is up here, or maybe it's over here. I'm not really sure. But, we can talk about the maximum in that case. We say we're going to look at every point between here and here, then there is a maximum. And we're going to have the same kind of situation in that other picture. So we're not going to, so we admit there's no maximum in an unconstrained way. If there's no further constraints, we just say, where's the maximum of this function? There's no maximum. But if we restrict ourselves to a certain domain, now here, we wouldn't restrict, in this picture, we wouldn't restrict ourselves just by just the x variable, or not typically, but we want to put a restriction on both the x and the y. So you know what that looks like. This is the z-axis, and this is the x-axis, and maybe the y-axis is coming out. And so we're going to restrict the domain of the function to a certain set of values, and then maybe there will be a maximum for this function. Probably there is one. So here, the so-called constraint is a little bit different than you might expect, because you might expect that the constraint is sort of a circle in the xy plane, but everything inside the circle as well. But here, that's not what they're saying. Here they're saying the constraint is just the circle. Okay, so all the points on on some circle in the xy plane, and this is the unit circle, I think you can recognize, but whatever the constraint is, anyway, it's just going to be like a kind of a linear constraint. It's not all the points in the xy, I'm sorry, in the unit circle. It's just a point, or what should I say? What's the right language? Maybe that's called the unit disk. So it's not all the points in the unit disk. It's just the edge points. In other words, just the circle itself. So that's what this says. If we said less than or equal to, that would be all the points inside the circle as well. But that's not the problem. That's not what they're asking us to do. They're not saying find the maximum for all points inside the circle and this circle in the xy plane. They're saying just on the xy plane. So it's kind of a stronger restraint because we're limiting ourselves more. Anyway, whatever it is, that's the kind of problem we're trying to do here. So it's pretty similar to this. We're limiting ourselves, so like limiting ourselves to just this region, or actually what we could do is just limit ourselves just to this point and this point. That's kind of what's the analogous limitation when we say just the circle. But whatever the limitation is, there's some limitation on the input space. In this case, the input space is just x, but in the picture, the input space would be x and y because those are the inputs. So in this picture, he kind of tries to draw the shape that this limitation imposes on this curve, this blue surface. So it's not a curve, it's a surface. So in other words, as I said, we have a circular limitation on the input space, on the xy, and then that means, at one of the points on the circle, the height is here, and another point on the circle, the height is up here, and another point on the circle, the height is down here. So we have this kind of uh, object that we're trying to find the maximum height of, and then he sort of turns it around and he sort of rotates this whole picture so that we can look down on it and we get this picture. So we have the unit circle, and then we have the contour lines, all these contour lines, which are the heights. So every point on a contour line, as we've discussed, every point on a contour line has the same height above it for the surface. So that's what these are. These are kind of equivalue lines here, because they say that every point on here has the same height or the same value. So actually there's some more here. There's one drawn here and one drawn here and so on. And of course, as we move out in this direction, the surface that we were talking about gets higher and higher, because that's what this picture looks like. As we move out, things get higher and higher, at least in this direction. I guess it doesn't happen in this direction, and also in this direction. I guess if we move in this direction, it gets lower and lower. But anyway, in some directions, it gets higher and higher. And so as we move out, we're getting higher and higher, which we want to do. We want to get higher and higher. But there's not going to be any maximum if we don't have any constraints. But we do have some constraints, and so there probably will be a maximum. So we want to move out, 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 but we can't move past the red constraint. That's where in fact, we can't even move. We're not even allowed to be in here, because we have to be on the circle. That's because it says equals, not less than or equal to. So, but anyway, we can see that at different points on the circle, we're going to have different heights. So we need to find the highest point when the xy coordinates are on the circle. So in the video, he says, well, what about if we think about f of xy equals 2, that is, this equals 2. So that means that there's we're talking about cutting the surface at height 2. So we imagine taking a plane that's parallel to the xy plane and has a height of 2, and just looking at where it cuts the surface. And that will be, if we look down on that, we'll see all the xy points that have a height of 2. So maybe this is the set of points that where the height is 2, and this. So maybe we can do better than 2. So if we look at f of xy equals 3, maybe it'll look kind of like this. So it will cut the circle. It'll still cut the circle. It'll still touch the circle. So that means somewhere on the circle, f of xy is equal to 3. And so we want to, as we said, we want to sort of move out. So here he moves a little bit further out, and here he's moved too far out. So we might get high values for the height of the surface, but we're not satisfying the constraint. So we've moved too far away, or too far out. So this is the perfect place to be, because if we go any further out, we're not going to be on the constraint. We're going to not be obeying the constraint. But we've moved as far out as we can. In other words, we've made the function as high as possible. And so we see that right here would probably be the best point, or maybe right here would also work just as well. So that's the idea visually. But the question is, how do we find this? How do we find this point? So that's not easy. But the solution, I guess, came from this French mathematician. Apparently he was born in Italy, but his was French. So anyway, his name was Lagrange, and he somehow understood one further detail about this picture. Now, it's not exactly 100% clear to me that his observation is right, but that's due to my own limitations, I guess. But anyway, what he said is that when you reach the place where they just touch, their tangent lines are going to be the same. In other words, the slope of the, what is color is this? The blue curve and the slope of the red curve, when they just touch, the slope or the tangent line will be exactly the same. So that's his insight into this problem, which it certainly looks possible, but I'm not 100% sure that it's true, but maybe there's some other way to show that it is true. But that's the insight anyway that will allow us to find which point it is. Let's go on to the next video and maybe we'll have a nice picture of that. So here's this picture again in the next video, and here he kind of blows it up a little bit, and he's trying to show in this zoomed in version that it looks plausible that the slopes are the same right where they touch. Now, just a few minutes ago, we made the argument that the normal vector to any tangent to any line will be perpendicular to the line. And that's sort of what this is showing. Because if you take this curve, for example, you can think, oh, there are many different tangent lines on this curve. So you can imagine there's a tangent line right here, another tangent line here, and another tangent line here. And we know that for any of those tangent lines, we can draw a normal vector, and that will be perpendicular. And we know how to get that normal given a particular tangent line. We just take the A and the B as we described it before, and take those coordinates, and those will be the vector that is normal. So in this picture, also, I can take the normal right here for this tangent, and I can look at another tangent, normal, and I can look at another tangent and normal, and right here I can look at a tangent, and the normal will be pointing in this way. And then for this blue line, I can do the same thing. I can take, here's a tangent, normal, or maybe normal would go this way, but it doesn't really matter. It's just perpendicular is what we want. And another tangent line here, normal in this direction or in this direction. And right here, same thing. So we can rephrase Lagrange's insight. Instead of saying that the tangent lines are the same at this point, we can say that the normal lines are the same, or at least they're in the same direction. Maybe one points this way and one points this way, but they're parallel to each other, or they're multiples of one another. So that's kind of a nicer, sort of a nicer way to rephrase what Lagrange said, or what he saw, which is that the tangent lines are the same, or the slopes are the same, or the normals are the same, or actually more carefully, that they are multiple. One is a multiple of the other one. Okay, so there's one more thing we want to say, which we've also already covered, and that is we talked about the gradient already. And we said that the gradient tells us the direction of greatest increase. So suppose we're right here, right on this here. Now if I walk in this direction, I'm not changing the height at all, right? That's what this contour line means. I mean, every point on here has the same height. The surface is the same height at every point on this curve. So if I'm right, where did I say? If I'm right here and I walk in this direction, I'm not changing the height at all. So that is definitely not the direction of the gradient, because the gradient will give us the most increase, and this gives us 0 increase. And the same way here, if I walk in this direction, that's not going to give me any increase either. So that is definitely not the direction of the gradient, because as I said, the gradient gives us the direction of greatest increase. So what is the direction of the gradient, say right anywhere, right here, right anywhere? So it's pretty clear that the gradient is the normal. Yeah, is the normal to the curve at that particular point. By the normal, I mean you take the tangent line at that point, and then we can talk about the normal to that tangent line, the vector which um, is perpendicular to that tangent line. So that's what I mean by the normal. And it's pretty clear that the direction of greatest ascent or increase is in that direction. So that's one more maybe observation. I'm not sure if that comes from Lagrange or not, but maybe it does. Or anyway, it's a very good observation. So the gradient is the direction of greatest ascent, and that will be the normal vector to the curve at the particular point. And remember, that sounds a little bit strange, but what we mean by the normal is we draw the tangent line there, and then we can talk about the normal of that tangent line, and that's what we mean by the normal at this particular point on the curve. So now we just want to write all of this down. So first, over here, this is the direction of the gradient for the blue one. And maybe the direction of the gradient for the red one is maybe just the opposite, but as we said, it's going to be a multiple of the blue one. Maybe it's the negative multiple, and it doesn't have to be the same length, but it's going to be in this direction, one of these two directions. So we said that the slopes are equal, or the tangent lines are the same, and then we turned that into that the normal vectors point in the same direction or are multiples of each other, and then we turned that and we said that the gradient is in the direction of the normal, so the gradients are multiples of each other. So the gradient for the one curve and the gradient for the other curve are multiples of each other. That's what we want to write down. Let's see where he writes that. First of all, he draws another gradient for the red one. He has it pointing in the same direction. And finally, he writes the equation that we wanted to say. The gradient of the blue one is just a multiple of the gradient of the red one. And this is the expression for Lagrange multipliers. And this will give us the extra piece of information we need to find the maximum value on the curve. Remember what the picture looked like. We had this picture, but we said, and so we say, oh, the maximum's right here, but how do we know? What are the coordinates of this point? So, you know, it looks nice as a picture, but that we're not satisfied with the picture. We want to know the actual coordinates, and that you can't get from the picture, right? You don't know exactly what the coordinates are. But now with this extra observation, it will give us enough information to find the coordinates of the point. So this is this is what leads us to the solution to our original question. Okay, so that's kind of it. But now we want to sort of work it all out. Use all these observations to actually do it. Maybe do a particular problem. So now remember that the gradient is actually a vector. So here you can see that it was a vector. Now, in our case, it's just a vector with two components. In general, it could have more components if we had more input variables. But in our example, in the picture that we were working with, we only had two components. So when we write this equation here, this is a vector equation because this is a vector of two components, and this is a vector of two components. Now, we haven't usually written vectors like as vertical. We usually wrote them as like this, as horizontal pairs, but there's no reason why we couldn't write it like that. So instead of writing them next to each other, we could write them like this, one on top of the other. So that's the way he's going to write it. But the point is that this is a vector and this is a vector. This is a scalar, but this is a vector and this is a vector. So remember, way back when we talked about what we mean when two vectors are equal, we mean that they have to be equal component by component. For example, if I said this vector was equal to this vector, I mean they're equal component by component. Now I should write this one vertically because it's just easier to see what I'm talking about. So I'm sorry for this big mess, but I'm just saying that this vector is equal to this means that these two are equal and these two are equal. That's what he's going to do. So he writes it out, the gradient of g. What does that mean? That means the partial of this g, remember g was this. Actually, we didn't say that. Well, I think we said it somewhere, or we didn't say it, but it was kind of understood that it was the circle. So this is g, and we want the partial derivative of g with respect to x and the partial derivative of g with respect to y. Now, there's one last thing. I don't think he said it, or maybe we skipped it, but g is not quite equal to x squared plus y squared. It's actually equal to x squared plus y squared minus 1. That's how he defines g. So he moves this over to the other side. But that doesn't, well, so then if we take the derivative, the partial derivative of that, I don't have the equal sign here. I make this minus 1 equals 0. And if I take the partial derivative of this with respect to x, I just get 2x. And with respect to y, I get 2y. So that's what he has here. And then we're going to put a lambda in front of it. And then we have to do the partial derivative of f, which can't really read it here, but it's x squared plus y squared. I'm sorry, x squared times y, and that's f. And we want the same thing, the gradient of that, which means the partial with respect to x and the partial with respect to y. And we end up with this. And this is kind of the gradient representation, or the vector representation of that gradient, that observations about the gradients being multiples of each other. But once again, when these are equal to each other, it means that this has to equal this times lambda, and this has to equal this times lambda. So that's two equations, which look like this. Now that's nice, but the problem is we have two equations, but we have really three unknowns here, x, y, and lambda. So that's why we don't actually have enough information written down here yet to make this solvable. But don't forget that we have one more equation, which is that. This is also part of the system. So now we have three equations and three unknowns. Probably we can solve this and find x and y, which is what we wanted to do. We wanted to find where on the circle it's going to be a maximum. The height of the surface is going to be a maximum. And that is the idea behind Lagrange multipliers. So we get this system and we just have to solve it, and hopefully we can. So we can see that maybe we can solve, actual problems like this one. We can find the actual x and the y. But what I want to stress right now is that we had um, a an equation subject to a constraint, and somehow we managed to put all of that into sort of one bigger equation and try and maximize that whole equation. So that was a little bit puzzling to me when I first saw it. Like, how can we take an equation and sometimes this is less than or equal to, so that kind of constraint, and make it into a single equation. Now, we didn't do less than or equal to. That turns out to be trickier to do, but we talked about this. Okay, so maybe we can do a problem, or maybe we can actually do this problem, and he actually does this problem. You can watch it and see the actual solution.